Hi, everyone. I hope everybody had a great lunch. So now we are starting our afternoon session of the Progress Workshop, and we are very happy that we have here today Dr. Yuejie Chi from CMU. A few things about Dr. Chi. She received her PhD and MA in electrical engineering from Princeton and BE in electrical engineering from Tsinghua University in Beijing. And she's currently the Sense of Wonder Group Endowed Professor of Electrical and Computer Engineering in AI Systems at Carnegie Mellon University, with courtesy appointments in the Machine Learning Department and Scilab. Her research interests lie in the theoretical and algorithmic foundations of data science, signal processing, machine learning, and inverse problems, with applications in sensing, imaging, decision-making, and societal problems broadly defined. And she has received various awards, including the PICASS Award. She has been a distinguished lecturer of the IEEE. We are really happy that we have her with us today. And without further ado, thank you so much.
All right. Thank you so much, Dora, for the nice introduction. So I'm very happy to be here in Greece and to share some of our recent work with you. So today I'll be talking about how to accelerate your condition low rank estimation. The key word is to use preconditioning. All right, so we have a lot of data coming from also have sensors, computing platforms, imaging systems, and so on and so forth. And this large amount of data has brought lots of exciting opportunities. But in order to tap into these new opportunities, we also need new tools that sort of are efficient and scalable in their use of computation and memory. And fortunately, a lot of data that we collect have low dimensional structures. I think for our community, it's probably not much needed for motivation that many of the data we collect has some sort of low rank structure where they can sort as embedding or encoding some latent structures where there's only a small number of interesting ones. So this kind of low dimensional structure kind of become ubiquitous across a lot of different applications we deal with across imaging, recommendation systems, community detection, bioinformatics, and so on. In this talk, we'll be thinking about a canonical problem that I call low-rank matrix sensing to start our discussion. So imagine you have some big data matrix M of size, say, N1 by N2, but fortunately, the rank of this matrix is small, say rank is R. Instead of directly observing this matrix, rather you'll be taking some sort of linear measurements of this matrix modeled by some linear map A, resulting in a collection of measurements M. Y that has dimension M. So typically, we'll be interested in solving this problem in the so-called sample-starved regime, namely the sensing budget, the number of measurements you have is usually much smaller than the ambient dimension of the matrix, but maybe just barely larger than the degrees of freedom of prescribing this low-rank structure. So we really need to leverage the low-rank structure if we want to solve this problem in a sort of faithful manner. And one intuitive approach is essentially trying to search among all the possible matrices and find the one that has the smallest rank that produces consistent measurements. Unfortunately, this kind of rank minimization is typically NP hard and impossible to solve. So there has been a lot of research going on trying to work around this by doing a convex relaxation. By instead of minimizing the rank, we can minimize the so-called nuclear norm, which is sort of the tightest convex relaxation you can come up for this kind of problem. And significant research has been put into this in general in the last decade, where we have been seeing a lot of nice statistical guarantees for this problem, where in many cases, this sort of convex relaxation solver can actually achieve near optimal minimax rate in terms of errors. However, this program is not necessarily scalable, because after all, this is a semi-definite program prescribed in terms of the ambient dimensions of matrix. So the complexity tends to be at least cubic with respect to the ambient dimension. And therefore, they have very terrible scalability when we want to work with large-scale problems. So in order to go beyond this kind of scalability issues, one resort to an alternative approach based on factorization. So if I know the rank of the matrix I'm looking for has some rank R, so maybe I can search among all the rank R matrices so that it has the smallest squared L2 error or least square error on my measurements. And this, I can directly tap into this low rank structure by rewriting this matrix C into multiplication of two tall factor matrices X and Y. And in doing so, I essentially rewrite the problem I'm interested in into an unconstrained optimization problem over the factor matrices X and Y. So the nice thing here is if you look at the bottom problem, this problem is much more scalable because we are only optimizing over these factor matrices that has complexity proportional to the degrees of freedom of the problem. But nonetheless, we now end up having a highly non-convex problem because this factors is actually not uniquely identifiable up to some invertible transforms. And speaking of non-convex optimizations, traditionally from the optimization perspective, they tend to be deemed to be somewhat tricky to solve and be hard in the sense, even for very simple problems that might be exponentially many bad local minima in the objective function. Nonetheless, in practice, people routinely solve these problems using very simple algorithms. So what actually saves the day as we'll showcase at least in this work is the statistical models come into rescue in the sense rather than arguing about the worst case performance of our problem, we want to realize that actually often the data or the problem we are facing in practice are working on data that come from real life that are maybe drawn from some underlying statistical mechanism. So therefore, if you try to leverage these underlying statistical models beneath your objective function, instead of looking at all the possible realizations, you can maybe focus on average, what is the most probable construction of your loss function look like. And that turns out to be often much more benign, so that even very simple algorithms like vanilla gradient descent can actually be very efficient. So vanilla gradient descent in the most naive form will be simply trying to optimize our parameters along the descent directions of an objective function with some learning rate or step size. Indeed, this line of thinking has been very fruitful. So putting this back into this matrix sensing problem I mentioned earlier, one typical result people have is basically trying to solve this factorization objective function, often with some little bit help that try to balance the size of the two factor matrices called balancing regularization. And with this regularization in place, we can actually come up with a strategy that solves the problem in two steps. So the first step is trying to come up with a good initialization, typically based on spectrum method, that try to come up with a pair of factors that's not too far from the optimal point. But the initialization by itself is not a sufficiently good enough estimate. And once you have this initialization actually lands in this so-called basin of attraction, so that from that initialization, you can just run simple vanilla gradient descent, and that will hopefully give you good performance. So in this talk, I will not be focusing on the initialization part, but we'll just have to ask you to trust me that you can come up with good initialization for this problem. And this is kind of a warm-up kind of a result from the prior literature on the problem that's been developed a couple of years ago. So imagining you have this low rank matrix M that is rank R and has a condition number, which is a kappa that is a ratio of the largest singular value and the smallest non-zero singular value. And then for this counter sensing problem, you can actually show vanilla gradient descent achieve some epsilon accuracy within a number of iterations on the order of kappa log 1 over epsilon, as long as the sample size is fairly larger than the degrees of freedom of this low rank matrix up to some polynomial order with the rank and the condition number. So this kind of result actually has been established in the for many other type of low rank problems as well, such as matrix completion, robust PC, and so on and so forth. So it's probably fair to say that we have developed pretty good understanding about the performance of vanilla gradient descent for solving such low rank matrix sensing problem. Even though it's highly non-convex, we can actually get very nice global convergence results. So this seems to be all nice, but this is actually just the beginning of our investigation. One thing as someone who works on signal processing is that we know that a lot of the problems we are dealing with in real world are often yield conditioned. And in fact, if you take this very simple loss function for matrix completion, and you keep everything to be the same, but just changing the spectrum of the underlying matrix to vary its condition number, we see the convergence rate of vanilla gradient descent indeed degenerates quite fast at a linear rate with respect to the condition number. So that dependency on the condition number in the convergence rate is not an artifact of the analysis, but indeed is a real indication about performance degeneration of vanilla GD when you have bad conditioning. So a natural question we want to look at is, can we actually accelerate this? Before I actually do that, let me just give you a little bit more motivation why we care about condition number. Instead of going through all the possible applications, let me just show you one toy data example to illustrate this issue. So imagining you have some, maybe this is just data set I downloaded from some website that measures chlorine concentration levels across 120 junctions over 180 time slots. So this is really just a data matrix of size 120 and 180. And indeed, as what we have been predicting, many of the data indeed have near-line structures, which can be manifested by plotting a spectrum in this decay form. So it has this so-called power law decay spectrum. So if I want to approximate this matrix using a rank 5 low rank approximation, this captures about 88% of the total energy and give me a condition number around 20. And if I want to capture more energy by doing a rank 10 matrix approximation, this gives me another condition number that is on the order 60. So this condition number may not seem to be terrible, but the key idea or the key message here is even for this very sort of innocent looking data, the condition number can be indeed very sort of larger than the rank or even comparable to the ambient dimension of the matrix. So in terms of the computation, we really shouldn't be ignoring the impacts of the condition number in our computation efficiency. Okay. So with this, this is sort of the question we want to motivate ourselves to consider: can we actually accelerate the convergence of gradient descent to a rate that's sort of independent with the condition number? Now, we want to stay with the first order gradient type of algorithm because we like all the nice things it brings in terms of, for example, machine learning, where you could easily have many distributed machines calculating local gradients and then doing global aggregation. So we want to stay with the paradigm of gradient descent type of algorithms, but trying to see whether we can actually accelerate convergence by getting rid of the condition number. All right, so that's sort of the question we want to answer. And in this talk, we'll be essentially examining this question in several aspects. We'll start with this sort of matrix estimation problem and give you a provable design that is insensitive to the condition number. And once we have sort of answer for that basic question, we'll try to generalize our analysis by looking at can we actually extend the idea to further develop algorithms that are also robust when the measurements can potentially be contaminated by adversarial outliers. We then want to extend to higher dimensional objects such as tensors and see whether this kind of idea can be applicable there as well. Finally, we'll actually try to go beyond this paradigm of having a spectral initialization and exact parameterization and try to understand, can we still succeed when the rank are potentially misspecified? So that's sort of our agenda. And with that in place, let me start with the first part. And this is joint work with my former student, Tian, who's now graduated and joined Amazon, and my colleague, Kong, from University of Chicago. All right. So this is our design, and this is probably the most important slide in this talk. we come up with algorithms that we call scaled gradient descent. And as the name suggested, we are essentially maintaining the algorithmic idea of gradient descent, but adding this sort of scaling or preconditioning into it. And we are not changing the spectral initialization. And we also don't need to add any balancing regularization. So we work directly with this vanilla least square laws. And what this algorithm looks like is essentially the following. So imagine you have two factors, x and y. You're going to update these two factors simultaneously. And if you don't have these red terms, these are just the vanilla gradient updates. But instead of doing vanilla gradient updates, I'm going to pull information from the red factor. Say I'm going to use y, construct y transpose y. So y is a tall matrix. So y transpose y is a tiny R by R matrix. So computing its inverse is not going to be expensive. In fact, often you can also combine it with calculations of gradient. So it's actually only adding a very small overhead to our calculations of gradient. And you are going to use this preconditioner to precondition your update for the left factor x. Now, similarly, you construct x transpose x, take an inverse, and use this to precondition the update for the factor y. All right, so that's the algorithm. And in fact, this can be thought as a preconditioned gradient method. If you vectorize your parameters, this preconditioner essentially pop up in the front of your gradient. So you can think of this also as some kind of quasi-Newton type of update. Now, how does it perform? Interestingly, when we put this on the sort of toy example we had before, we see that this new algorithm, scale GD, actually converge at a condition number independent rate. And all this convergence curve lay on top perfectly on the convergence rate of vanilla gradient descent, as if you have perfect condition number equals 1. But whenever the condition number is larger, scale GD is provably faster. So what this suggests is if you have a highly U condition problem, scale GD can potentially give you a huge computational saving by accelerating the convergence rate with only a minimum overhead added on top of each of the gradient computation. So the algorithm recipe seems to be very simple and seems to work. And you may wonder, why does this work, right? Intuitively, there's maybe several reasons, and this is kind of one of the nice intuition behind this algorithm. That is, this algorithm actually has some kind of nice scale invariant property. So remember that in this low rank estimation problems, these factor matrices are actually not uniquely specified. You can actually introduce, say, some invertible matrix Q, multiply it to one of the factor, multiply its inverse transpose to the other factor, that still give you the same low rank matrix. So from the representation perspective, you shouldn't be favoring one with respect to the other. However, if you're running gradient descent from either of these points, the updates can be actually quite different. You get very different trajectories of the algorithm. So the update of scale, the update of vanilla gradient descent can be very sensitive about how you actually scale these two factors. On the other end, what scale GD does is, if you take, no matter which factor you are taking, your next iterate will be actually covariate with respect to this change of parameterization. So if you change the parameterization as iterate T using some matrix Q, the same matrix Q will pop up in the next iterate. So in other words, you can essentially or almost think about scale GD as a manifold optimization algorithm, where it sketches out the same update in the low rank matrix manifold. And this is one of the key properties of this algorithm. And of course, to get really the convergence rate that we want, there's a lot that needs to be done in terms of analysis. And one key idea that is useful when analyzing this kind of preconditioned algorithm is that you actually need to come up with the new distance metrics to serve as a Lyapunov function to bound the sort of per-iteration progress of your algorithm. So this distance actually need to take into account as a preconditioning, and together with a very careful trajectory-based analysis. So with these ingredients in place, we can actually have a convergence guarantee for our scale GD algorithm for the same low-rank matrix sensing problem that will show this algorithm actually converge probably in a number of iterations that's on the order log 1 over epsilon. So it probably eliminates the condition number in the convergence rate at essentially the same sample requirement as the previous GD algorithm. So this is some sort of strict improvement over the prior results for vanilla gradient descent, because we essentially allow us to say computation without hurting the statistical performance. In fact, this recipe is quite general. You can apply this to a lot of other problems as well, such as robust PCA, matrix completion, and so on. And the message is also pretty similar, that essentially under comparable statistical requirements, we can probably improve the iteration complexity of gradient descent by eliminating the dependency on the condition number in the iteration complexity. Okay, so that's sort of our basic recipe for the estimating the low rank matrices by using this scaled gradient descent idea. And the natural idea to sort of extend this approach is to actually look at, can we also extend the idea to non-smooth problem? And this sort of also allow us to deal with the existence of outliers or corruptions in our measurement model. So let me explain this a little bit. So imagining potentially when you are taking this measurement pipeline, due to potentially maybe sensor failures or malicious attacks, maybe some of your measurements can be potentially corrupted by some outliers. Yeah. Yeah. So this result is for sensing. So, but we have also results for completion in the paper. It's just not, yeah. Yeah, it's in the paper, yeah. For non-convex is NR square, and that the square comes from spectral initialization. Yeah, because you need the spectral initialization. Yeah. There's no NR result for non-convex. Yeah, sure. All right, so this is a corrupted model where essentially introduce this outlier factor, which can be arbitrary, but we say only a small fraction of this outlier can be non-zero. So alpha here is a fraction of the outliers. Now, whenever you have outliers in your measurement model, the least square objective is no longer appropriate because you can have arbitrary corruptions. Nonetheless, we can actually result to the R1 loss, the so-called least absolute deviation loss, that try to optimize this objective function over that has this R1 norm form over the measurement residue. Now, the additional challenge when dealing with this problem is the loss function become additionally non-smooth. But nonetheless, the two-step recipe that we talked about earlier still more or less applies with some sort of specialized modification to deal with the existence of outliers. For example, in the initialization, you may need to do some sort of robust statistics guided approach. And in the local updates, instead of using the gradient, you may have to use the subgradients. But this approach suffers from similar slowdown due to yield conditioning. And as you can probably predict, what I'm going to do now is basically instead of using the vanilla scale, the vanilla subgradient iterations, I'm actually going to add in my preconditioners here in basically the same manner. I'm going to precondition the left matrix using Y transpose Y inverse, precondition the right factor Y using X transpose X inverse. And typically with subgradient methods, your learning rate cannot be constant, but there need to be somewhat carefully set that some maybe polyak or geometrically decaying learning rates. And with this all in place, and turned out that we can essentially deliver a very similar message as a smooth case. And here it's just trying to benchmark our results with some of the previous results on subgradient methods, where for simplicity, I'm only highlighting the iteration complexity for problems such as matrix sensing or quadratic sensing, where again, we can probably accelerate the convergence by a factor of the condition number. So with this sort of subgradient methods, we essentially allow ourselves to solve this kind of low-rank matrix estimation problems with a robust property that is kind of double robustness to both underlying new conditioning of the low-rank matrix and also adversarial corruptions in your measurements. So we kind of achieve the best of both worlds in this setup. All right, so this seems straightforward. Let's now move to tensors. Now, tensors actually turned out to be quite interesting. And this is another set of paper jointly with Tian, Kong, and also my new PhD student, Harry at CMU. And we now have a lot of data that are sort of not just matrices, but the tensor data that are capturing sort of multi-directional, multi-way interactions of data across different modalities. By using tensor decompositions rather than trying to unfold this data into matrix forms, it is possible to capture this sort of multi-dimensional interactions and deliver insights that are not available when you are using matrix methods. So there are actually a lot of interest in looking at tensor data. So similarly, well, so for tensors, there's actually not only one possible way you can do a low-rank decomposition. Now, in this talk, I'm going to take this so-called Tucker decomposition that's defined by this very complicated looking equation that I don't want to get into this definition, but pictorially, this is really what we are trying to do. Instead of representing this high dimensional tensor directly, I want to represent this using 3 tall matrices, U, V, W, each kind of tell you the subspace of the data that belongs to in that dimension. And we have this very small, tiny core tensor in the middle, where each of the dimension can be thought as the rank along each of the modality. So instead of directly estimating the matrix T, so the tensor T, we'll be thinking about estimating this factor matrices and the core tensor. So this is another sort of multi-linear representation, right? While in the matrix case, we only have 2 factors, but now we have essentially 4 factors that we are dealing with. All right. And the sort of the canonical problem here, again, is this kind of low-rank tensor recovery problem. That is, given maybe some linear measurements of the tensor, I want to be able to recover this tensor. And surprisingly, tensor problem seems to be much, much more challenging than its matrix counterpart. And some of the potential reasons might be the following. So the first one is computational hardness. So we know that for matrices, we can result to convex relaxation, such as a nuclear null minimization. But turns out that the convex relaxation for tensor rank turned out to be NP hard to compute. So even you do convex relaxation, it doesn't mean you can solve it in a computational tractable manner. So it's also a wide belief in terms of the so-called computational statistical barriers by connecting this to some sort of hardness conjecture people have in computation complexity theory. It is believed that you can only come up with polynomial time algorithms for tensor recovery when the sample size is above the order of n to the 1.5 order. And in fact, if you count the degrees of freedom of a low-rank tensor, it's only linear in n. So this n to the 1.5 order is strictly above the number of measurements you need to prescribe the tensor in an information theoretic manner. Finally, when we start working on the problem, there seems to be very little existing results for the Tucker case. There has been some results for example, the case with CP decomposition. But for the Tucker case, there is actually no provably efficient first-order algorithm for low-rank tensor completion under Tucker decomposition. There is one nice paper by Willard et al. Where they look at the sensing problem using gradient descent that I'll also mention a little bit later. So this is sort of our goal. And we want to actually look at this problem and generalize our idea of designing scaled gradient for tensor problems. And how to do this for tensors? It's not immediately clear, but we know how to do it for matrices. So why don't we maybe try to unfold our tensor into a matrix form? So if I unfold my tensor maybe around the first mode, this actually allows me to write this as a matrix multiplication, where the left factor is U, and the right factor actually write up all the information from the other factors. Let's say I call U brev. So if I want to write down the scaled gradient update for the factor U, I could just think about this as a matrix thing, and where the preconditioner is going to be designed using information from U brev. So I just take U brev transpose U brev inverse to precondition it. So I can actually do this for all the factors UVW. There's one last thing, that is how to update the call tensor. And that I can't directly use this intuition, but it turned out that this is something about the invariance and properties. So that actually this is how we want to update the call tensor. Okay, so if you put this together, you get this very complicated looking thing for the algorithm. This is kind of unavoidable working with tensors that once you raise the dimension, the complexity notation actually also scales exponentially. But again, the key property is with this update rule, we get the similar kind of invariance property with respect to parameterizations of this factor UVWS, where if you think about all the invertible transforms. All right, so with this algorithm, we actually show the performance. We show in the paper, we show both for sensing and completion. So here I'm actually showing the result for the completion case. And again, the key message is we were able to get result where the computational complexity is on the order log 1 over epsilon. So probably independent with condition numbers. As long as the sample size is on the order of n to the 1.5 order up to some polynomial factors with other things. So again, this actually gives you the first probable linear convergence at a near optimal sample complexity for this kind of problem. Now, if you look at the performance, this is basically very similar to the one that we've seen for the matrix case, where the convergence rate of our scale GD algorithm is very fast. Well, if you run the regularized vanilla GD algorithm from the previous paper by Willard et al. For this completion problem, even though they don't show guarantee for completion, this algorithm actually also suffers from performance degeneration with a condition number. Now, in fact, if you plot the convergence rate as a function of the condition number, the convergence rate for this tensor problem for vanilla GD actually depends quadratically with the condition number. So you actually suffer even more with bad conditioning when you're working with higher dimensional objects. Well, our algorithm actually has a constant scaling regardless of the choice of our condition number. So the benefit of using this kind of scaled updates is more evident when you are working with tensor or higher dimensional problems. All right. I don't know how much time I have because we sort of lose some time in the beginning. Okay, good. Yeah, so well, I'll actually skip this. Maybe I will say a couple of things. Okay, so we actually also work on this sort of tensor problem on this application called robust PCA, where you can essentially generalize the scale GD algorithm design to additionally handle corruption and outliers in your tensors. And one of the interesting thing I want to show is actually this sort of connection to maybe some of the neural network and deep learning things. That all the algorithms that I've developed so far is kind of nice theoretically, but when you actually implement this algorithm in practice, for example, this RPCA algorithm, there's tons of tuning parameters in the algorithm in terms of how you want to tune your learning rates, how you want to construct some maybe thresholds to remove outliers at every iteration. And those are not necessarily easy to tune. So my student Harry came up with this approach that he basically takes this unfolding view of this kind of iterative algorithm and leverage the sort of self-supervised learning technique that does not use underlying ground truths, but just the incoming data alone to help to tune this hyperparameters in sort of a self-supervised way. And without sort of really much efforts, maybe with some efforts of the GPUs, we show that actually this approach delivers quite nice recovery guarantees when we apply this to some materials data set, where we can actually quite nicely separate a low-rank component from some of the saliency factors that our collaborators seem to have quite meaningful for their application domain without actually using any domain knowledge. So Harry will actually going to be presenting this paper at ICASSP, I think on Friday. So if you're interested, you can go through his presentation to learn more. So finally, let me just quickly talk about the last aspect about having over-parameterization in this approach. So for this, I'm going to actually revisit the matrix setting because it's sort of easier to set up the stage. So far, I have been sweeping importancing under the rug. That is, I'm assuming secretly I know the rank to use for my problem. And in fact, if you do not know the exact rank of the low rank matrix, this approach may fall apart in the sense, so if you do not know the exact rank, then what you could do in factorization is you over-parameterize. So instead of using the rank R, you parameterize using maybe some higher rank R prime and trying to recover this fatter factor matrix X using this kind of scale GD update. So this is for PSD case, so there's only one factor. And when you have over-parameterization, this factor matrix itself could become U-conditioned, so that this inverse, this preconditioner, become actually potentially unstable. And in the analysis will also break up. So in order to fix this issue, what we can do is kind of similar to what we usually do with regularization, Tikhonov type of regularization, is to add some identity matrix in this before we do inversion. And this helps to stabilize the preconditioner and make the algorithm stable again. So this is actually also connected to a lot of the observation or discussion people have in deep learning, because once you over-parameterize, we actually have infinite many global minima. So we can actually overfit the data, so the training error is always 0, but not all the matrices that are consistent with our observations are the low-rank matrix we want. So there's a separate question in terms of generalization. Can we actually guarantee generalization here? Now, this is particularly interesting for preconditioning because preconditioning is originally sort of considered or motivated to accelerate computation. But by accelerating computation, we do not necessarily know whether we are still converging to a solution that is generalizable. Are we accelerating but overfitting, right? So that's the question that's not clear. And in fact, this kind of question has been attracting a lot of attention in the machine learning community, where they try to study how preconditioning, how or hurt generalization. So our study here can also be thought as trying to answer this question, but for this kind of low rank estimation problems. And surprisingly, the answer is it actually does not hurt generalization. And indeed, we show that if you do the sensing problem, if you pick your regularization, your lambda, as on the same order as a minimum non-zero singular value of your low rank matrix, and And then if you use a very small initialization, a small random initialization, then you can actually guarantee that you also get epsilon accuracy within this number of iterations at sort of a comparable sample complexity as before. If you have exact parameterization, this analysis actually also give you perfect recovery when you are just using random initialization. So let me try to pass this convergence rate a little bit using a figure. So earlier, for this kind of low-rank sensing problem, there are also analysis done for gradient descent. And roughly speaking, both of these algorithm has this kind of two-stage convergence. Whereas the first stage is essentially somewhat like a feature learning stage, where you try to figure out the low-dimensional subspace for a low-rank matrix. And this part actually take a complexity that's polynomial with a condition number. But once you sort of learn the features, you enter into the nice local regime as we showed before, as if you have spectral initialization, and you get linear convergence. But actually, the dependency with the condition number is also worse. On the other end, with scale GD, we actually have this initial phase that only depends logarithmically with the condition number, ignoring some log dependency with the dimension. So in practice, often we actually hardly observe this stage. The algorithm often almost pick out the feature space in the constant number of iterations and converge. And once you learn the sort of the signal component, you will get back to the stage of local convergence and converge linearly at a condition number independent rate. So again, even in this over-parameterized settings, our scale GD algorithm it allows us to pick up the signal component at a much faster rate than GD from small random initialization. Yeah. Yeah, all these results depend on kappa, even for the earlier results. And this is kind of an analysis artifact. Even for vanilla gradient descent, the sample complexity has kappa. So for all the non-convex analysis in the literature, the dependency with R, as you pointed out earlier, is not optimal. And also there's dependency with condition number. Yeah. Yeah, so empirically with either GD or SGD, so scale GD. So the main difference of this algorithm is computation. In terms of sample use, empirically, they do not seem to be relying heavily on the condition number. Theoretically, yes, that's what you are seeing in all these results, in all the non-convex results. Yeah, for all the non-convex analysis. All right, so let me conclude quickly. So in this talk, I've been highlighting this approach that sort of advocating this preconditional design for low-rank estimation with the hope that to accelerate yield condition, the convergence in the yield condition case. Across the board, our hope is to design algorithms that are statistically near optimal in terms of sample use. Also computationally, that can achieve near dimension-free iteration complexity in terms of both problem dimension and the condition number, and has additional robustness with respect to adversarial outliers in yield conditioning. And we see that the key idea underneath a lot of the analysis is to exploit the additional problem structure and geometric property associated with these low-rank estimation problems, and go beyond just analyzing convergence of optimization algorithm using a black box approach by carefully addressing how the iterates progress along different iterations. And again, finally, we see even very simple variants of gradient descent allow us to achieve much faster and robust convergence compared to its vanilla version. And if you are interested, okay, so this is my slogan, preconditioning helps. You should try to think about how to design preconditioners for your own problem. Gradient descent often is very painfully slow. And right now we are actually trying to generalize this idea also to other problems. For example, one is the asymmetric case for the over parameterization setting. We are currently writing up the proof, but we are also leveraging this idea to other learning and estimation problems, such as spike deconvolution, super resolution. There are many potentially interesting directions to go. All right, so these are some of the publications we have, and I'll be happy to answer the questions. Thank you so much for your attention and for having me here. All right. So if there are no questions, I guess we're done. And feel free to ask me a question if you have other questions offline. Yeah.
Okay, thank you. I wanted to know is the condition on the rank for every iteration maintained?
Yeah, you use the same rank.
Do we always get it, or is it dependent upon the structure of the function or the gradient function?
So the rank is like an input parameter, right? If you know the exact rank, you can use the first version without over parameterization. If you have some, if you generally so this is actually a tricky question in terms of rank selection, right? For running this algorithm, it kind of depends on the problem, because generally speaking, your data may have maybe a spectrum that look like this. So you could argue that you don't really have exact parameterization. There's always a U-conditioned matrix, but this U-conditioning by itself can become very large if you do not add in the small regularization in the preconditioner. So at the end, that's some sort of design choice.
So in the gradient, in the iteration you gave, the equation where you do the preconditioning, is this the function f of xt yt, right? That
yeah, so f is this.
Right now, that is the cost function. Suppose I change that cost function.
You just update.
Can you maintain that the rank of yt plus 1 will remain the same as rank yt?
They will have the same shape, right? But if you have over parameterization, they can potentially become less stable, right? That's why you need to. They can potentially become rank deficient or close to rank deficient. That's why you add the lambda I in the preconditioner.
Okay.
Yeah.
Thank you.
All right. I think we're done. Thank you.
Challenges that we with confidence, and we are going to hear panel's members' experiences from their careers. So for this, we have Dr. Yuejie Chi from India Institute of Science and from IEEE. We have Dr. Zitan from George Mason University, Dr. Namrata Vaishnavi from Iowa State University, and Dr. Yuejie Chi from CMU. So thank you so much. We are looking forward to this.
All right, so I'm Ji Tian from George Mason University. So I'm going to be moderating the session. So I guess so the session is about navigating challenges in with confidence experiences in signal processing field. So we have several panelists who are very successful in the signal processing field. So we're going to share experience and we'll welcome your questions. I guess I'll start having each panelist telling a little bit about yourself so that they know a little bit about our experience. And if you have some afterwards, you have some questions, and feel free to ask. I guess we'll start.
I guess you already know me from my talk. All right, so yeah, so my name is Yuejie Chi. I'm from CMU. I finished, I guess I'll just tell a little bit about my personal career path so far. So I did my I grew up in China and I did my undergrad in Tsinghua University. And after undergrad, came here for a PhD at Princeton. And then I directly went for an academic position at Ohio State University. I stayed there for 5 years and I moved to CMU in 2018. In terms of research, I actually started my research initially. Actually, my advisor is Robert Caliban. He is not an he's not a single processing person per se. I think his primary area will be information theory and coding theory. So when I started working with him, I started actually with some waveform design for radars. And later compressive sensing becomes very popular and I kind of jump onto compressive sensing to work on a lot of problem for using compressive sensing for sensing problems. And that sort of also down me to some of this working on single processing problem with low rank, low dimensional structures. And more recently, I'm being also very interested in machine learning, starting to work on some of the federated learning, reinforcement learning problems.
Hi, everyone. I'm Namrata Vaswani. I grew up in India. I graduated from IIT Delhi with a bachelor's, and then I came to the US, pursue my PhD at the University of Maryland, College Park. I finished in 2004, and since 2005, I've been a professor at Iowa State University. My research has been in the broad area of statistical signal processing and machine learning on one end, and imaging applications on the other. A lot of my recent work has been, or last decade or so, work has been in compressive sensing and low rank matrix recovery. And yeah, that's that. Hi, this is Etienne. So I was born in China, so I got my bachelor's in the University of Science and Technology of China. Then I came to the States. I got my degree in George Mason University in 2000. Then I went to Michigan Tech for 11 years. And afterwards, I have 3 years at the National Science Foundation as a program director. After that, I returned to George Mason, my alma mater, as a professor. So most of my research is on estimation detection, signal processing. I look at signal processing for wireless communications and also in machine learning. So that's been over 20 years in SP.
Okay, hello everyone. I did not know that I was a panelist until a few minutes back. So anyway, my name is Hari. I graduated from Usmania University, Hyderabad. Then I did my master's at IIT Delhi, and then I did my PhD at UC San Diego. Started my work, research work in array signal processing. And over the years, the students have defined my research problems because they sort of come up with some new ideas. I give them the freedom to select a set of problems, and then we work together. So I continuously learn along with my students. So I have worked on compressed sensing. I work on applying these techniques, including deep learning, because without deep learning, students don't want to do any projects or any activity with faculty members nowadays. So I've also started learning, and we are applying these tools for communication, radar, joint radar communication systems, and also for healthcare applications.
All right, so anybody have a question that you want to ask? Take the chance, because we have a relatively short session. So if there's something in your mind, and we have people who may be able to help. Any questions from the audience? Just stand up and ask. Yeah, so part of the reasons we're having this workshop is we encourage junior researchers to SP field, and also we want to have the voice. So it's important to have your voice heard. So this is a informal setting, and this is your chance to practice. Okay. I guess we'll get started. So I have a number of questions from the organizers, so probably collected based on the feedback. So I'm going to start with some of the questions that I have, and I guess the first question is how to handle paper rejections. Anybody want to chime in with paper? Yeah.
Okay, yeah, so this is a very interesting question. My feedback is two things. Sometimes paper rejections, I mean, they feel bad, but sometimes the reviews are good. And actually, there's always something good in the reviews, even if the reviewers completely misunderstood what you're saying, that probably gives you feedback that you need to write your paper differently. This doesn't come easy. This isn't how I started. When early in my career, I used to take them really badly, and I used to take them personally sometimes. But over time, I've started seeing the good in even rejected papers. Now, there are certain situations where the rejection is completely unfair, in which case it is valid and there are processes to appeal. And appeals do get accepted. I do have, again, personal experience with that. There is, even though no journal openly says it on their website, there is a process to appeal a journal paper rejection. You start by emailing the editor-in-chief or the associated editor, depending on the journal, and go from there. And yeah, there is a fair process that if the editor-in-chief accepts your appeal, they will either invite extra reviewers or, there's a process in place. And again, from personal experience, it does work. So those are my two.
Yeah, I guess I also want to mention something about getting a paper rejection from conferences, because sometimes conferences, the reviewers are it's pretty diverse. So sometimes you get diverse reviews. Sometimes the reviews are not necessarily correct. Your paper get rejected. For young researchers, and it can be upset about the reject. You feel like your work is not approved. Actually, don't think that way. You see, actually, senior advisors, they're getting cool about paper rejection, especially conference paper rejections. So I always tell my students, if your paper get rejected, don't feel bad. It's not about your work, and take the feedback, try to submit somewhere else. Don't take it personally. Okay, so and I think that just keep going. Don't feel upset.
Add a little. I agree with all the things that have been said. One thing I want to mention is even the paper is rejected, but don't stop promoting your work, right? There's also other ways that you can put your work out there to get people see, even though it's not going to be maybe presented at this one conference, but you can maybe present this as a workshop, doing a poster presentation, or even put your code on GitHub, right? There's many different ways you can disseminate your work and let your work being seen by other people. In machine learning, there's tons of papers that we know that are not accepted by any of the major conferences, but are highly cited just by their archive preprint, right? Because people all know this is rejected paper, but it turns out to be widely used and followed by the community. And that's probably a better proof of the value of the paper than just acceptance.
All right, so any questions? So maybe the room is warm now, so any questions from the audience?
How did they take it?
And anybody wants to share your experience about getting paper rejected, how you react? Yes.
Hi, this is Shreya, and I'm also a PhD scholar. I don't have any rejection. Of course, I do have. I don't want to share that, but I just want to ask, what is what? Just a suggestion, maybe. What could be the better way? It should be a conference paper, or it could be a journal paper. It should be shorter version because in conference we have a limited pages to explain. So, what can be a good way to promote your work, or provide other information into the broader way or the shorter way? What is your suggestion? Just a kind question.
So are you talking about research particularly related to machine learning or to signal processing? Okay. Okay.
I don't know about the specific field, and I don't necessarily take these strategies myself, but I know a lot of people now have Twitter accounts, for example. You can certainly try to advocate your work in those public venues, and maintain a good homepage of yourself, right? This is a place that you own, and you can try to come up with very nice visuals to explain your research. Yeah.
Yeah. All right. So I guess I'll move on to the next question. How to choose a research advisor or a research topic or research lab? I guess that's for students who have not started the P. So do you have any of you who have not had advisor and deciding where to go? Or just raise your hand to see whether I can change the topic? No, so you already have an advisor, you have no choice. Do you want Okay, then let's focus on how to choose a research topic. Any comments?
No good answers. Oftentimes you start with doing something and it leads to something else. Or your advisor suggests a broad area. I don't think, at least for my students, or if I remember correctly for my own PhD, I don't think we first decided the title and then did the work. We just kept doing some work and eventually it morphed into a PhD thesis. So that's kind of how it's happened for most of my students also. So.
Yeah, I think the research has a lot of trial and errors, right? Most of the research projects don't pan out. The only one that really work out is just a small number of ideas that maybe you come up and actually works. I often think about the first couple of years of my students' PhD as somewhat a training phase that you are really if you think about yourself as a reinforcement learning algorithm, right? There's exploration versus exploitation. So initially in your PhD, you do more exploration, trying to play a little bit, maybe different problem formulation, get your hands dirty and see where your passion is and where sort of your expertise really work out, right? Because potentially there are problems that are important but very hard, or problems that are not important, very hard, or actually simple problems that are important. And so there's all these dimensions, right? Ideally, you want to work on simple problem, but important. Right? But those are really, really hard to find. Or if you're very capable, you work on hard problems that are also important. But that's really hard to tell a priori what problem is hard and what problem is important. So you do need to do a lot of exploration. And towards the maybe end of your PhD, you get a good idea and you can figure out maybe the right nice thesis topic that for you to make a contribution. So my suggestion is maybe set your expectation low initially. Don't just think that every problem I work on has to have a paper on it. Right? That's not going to be the case most of the time. And even you do get a paper, it may not be an important paper in retrospective, but focus on the learning part of the projects.
Just to add, so many of you may be graduating and maybe embarking on your next phase where you may have to become a research advisor to students, right? It's possible that you may be thinking about it. So very similar to your personal experience would have been maybe your advisor suggested something and then you liked it and you pursued. But if you are going to become an independent researcher, it's a good idea to follow whatever has been said, to explore and try to do things which are not related to, I mean, it's not closely related to what you have been doing. The tools may be similar, but try to do something different so that your peer community also recognizes that you can do independent research. Sometimes the question is that whether the advisor helped you do the research or you contributed, sometimes is not clear in publications. So it's a good idea for you to slightly go away and pick up a new topic and then learn whatever you have learned of how to do research, you apply it there. Establish yourself that you can do research in a new topic other than your PhD topic. That gives you confidence, that gives you breadth, and it helps in general your own quest for learning new things and being curious and so on and so forth. I think that is important for you to become slightly more open, and not getting the desired results is a fact of life and fact of research also. So it's not necessary that you will get always results which improve something or something is important. But the process of learning how to do research, I think, is more important, because 5 years from now, you don't know which topic is going to be the hot topic, right? But if you know how to do research, you will be able to easily handle that situation when a new problem presents to you to be tackled. So I think if you can concentrate on that part, it will help you throughout for your next 30 years of your professional life.
Yes.
How do you move from being supervised to doing your own research and having your own ideas? Like being supervised to having your own research and like.
Okay. I guess I echo with the panelists what have been said. So basically, at the beginning of the your research career, it's very likely your research is supervised, and at that stage, you're given a topic. Don't be too picky on the topic, as we said. Not all the papers, not all the topic will lead to a paper, but it's an important stage to learn to practice on your research skills. Learn how to do literature research, how to summarize your results, how to write your papers, or just a report. So the research skills, it also helps you to, through the process, when you are supervised, you want to take advantage of the help from your advisor to see why did the advisor pick the topic? Is it because it's important or is it because it's simple? So you get a sense what will be an important topic. So over the process, you'll be exposed to different topics and your research skills are growing. At that stage, you may be able to identify some topics by yourself. And at that stage, you can talk with your advisor to see, I'm interested in that. Can I do that? If you can justify why it's an important topic, most likely you'll get the support from your advisor and you work on that. So I think it will be a natural process, as other panelists says, that the research skills are very important. Part of the research skills are is identify what topic is important to work on, and that may come in a later stage of your PhD study. And yes.
Hi. So there's a lot of. So first, thank you very much for previous experiences sharing. And so previously, one of you mentioned that we can try some topics that is not in the main line of our PhD research that we can explore around. But on the other hand, probably in some circumstances, the supervisor supported us by some fundings, and which is related to a very constrained topic. And in this case, if we want to do something relevant but not that relevant, how can we get support from our supervisors and convince he or she to do this exploration. I hope
I guess I'll start, like the other Chinese. So at the beginning, as I said, we all said at the beginning, don't be too picky on the topic you're working on. Even on the, the supervisor has a project you need to work on, and even it's not very interesting for you at this point, but take it as a chance to practice your research skills. Hopefully through this project, you'll get a whole a spectrum of from literature research to executing research results to writing reports or paper. I think those are important research skills to be developed, and that can be based on the research projects that you're assigned to. Along the process, you accumulate certain research skills that are, research knowledge that is related to this project. So if you're developing research topics, it's likely that grows out of the research knowledge that you have. So hopefully something related to the project that the advisor is working on. Nowadays, coming from my point of view, there are many advisors always want to do some basic research, and even if you're they always want to balance. So you may want to convince the advisor this is the next project for the advisor to go for the next funding opportunities. So, and I guess it wouldn't be too far away from what you're currently working on, because that's where you develop your research knowledge. So I think that hopefully that's a smooth transition. Just don't be too picky at the beginning. Yeah. Anybody else?
So another thing, and this is for before you pick your advisor, generally speaking, if you pick advisors, so there are researchers who are primarily funded by, say, in the United States, I'll speak in the US context, where depends on the funding agency. If your advisor is primarily funded by the US National Science Foundation, then the research can be much more open-ended, and they're much more, whereas if it's certain kinds of defense funding is where their funding comes from, then you are kind of restricted to do what the grant or industry funding then it requires you to do. So maybe it's something to look at when you're trying to decide your PhD advisor. Another alternative is to pick a co-advisor who is NSF funded and or working in the area you want to work in, and a lot of people are happy to collaborate. Yeah, but it's a not an easy answer.
Just want to add that research is not confined only to during your PhD, right? You're embarking on a long journey of 20, 30 years. Even if it is industrial R&D, doesn't matter. It's research you're doing. So curiosity-driven work will be a long term. So what you learn during your PhD is how to do things, how to be disciplined, how to communicate effectively, both in writing and oral presentation and clarity of thought. All that happens during a PhD. And of course, you have to generate new results so that you can publish and contribute to the large body of knowledge. So if you can take a slightly longer term view, then you will enjoy what you're doing in your PhD because you're learning how to do things. So then you go to explore, do something else, etc. So these are always life is constrained. So because the contribution is important, whatever field you pick, right? So that contribution is important for you, the novelty part, etc.
Yeah, I guess one thing I can add, just my personal experience. My undergraduate, I was studying control theory. So when I was young and clueless, I thought I have to do research in control theory. So I was looking for people working on control, but that's the time that in the US, nobody's working on control. So I ended up working on array processing, which I had no clue. I didn't know how important it is, but turned out to be very fruitful. So sometimes when we are young, we don't have the experience. But having said that, I think picking the right advisor actually is important, because your advisor may know what's good for you. But at least when I was young, I didn't know what's good for me. So I think that's also something to keep in mind. Yeah.
like to add something.
Yes.
So this is a non-technical comment I'm making. Your advisor is going to be a very important part in your complete professional career. Okay. At every stage in your professional life, your PhD advisor's reference letter is sought. Okay. Whatever you do, whether it's a grant application, whatever, any reference letter, your PhD advisor is very important. So have a good relationship with your PhD advisor.
Actually, Hari, that's not always correct. That's very university specific. And
Okay.
Many places after your PhD, they don't, after your first job, they don't seek letters from your advisor.
Any other questions? Yeah. Yes. Mhm.
I guess when it comes to like having those maybe not so conventional ideas that you want to explore, do you often look at requests for proposals to see if it could fit somewhere that people are already thinking about, or do you like take a different path to explore how you could get that funded and explore that, I guess?
So are you talking from a student point of view or a professor point of view?
I guess transitioning to starting your own research point of
Okay.
view.
Okay, so you're early.
Yeah, just graduated, so.
Okay, all right, good, good. Good.
So, yeah, I guess when you first start your own group, you want to work on some new set of problems that also help you to distinguish yourself with a former advisor. Well, if you are assessing one of the good idea, a potentially good idea to see what other people are working on is to actually look at the award lists, for example, on ISF website. Then you get a good idea on what are sort of the trendy topics, what they are funding, and what everyone are working on. So you get some basic ideas. And not to say you are going to work on the same problems, but that may give you some idea. And maybe you want to work on similar problem. Maybe you want to actually avoid those problems. But that at least give you some sort of the intuition, right? Something to start with. And of course, I think initially you do still work on something related to your previous research. Personally, I don't advise people to completely abandon their track record and start something afresh. That's maybe very risky. But sort of continue on what you are already working on, and then maybe trying to bring in new things and new ingredients might be a good idea. So maybe you have working on one area, and now you want to bridge this. Maybe you are working on in some machine learning application. Maybe you want to bring in maybe fairness or some other aspects. So it's still leveraging your expertise, but bringing a new set of constraints, a new set of considerations might be a good initial point. Yeah.
Yeah. If you're starting off for a new career, I think you want to be balanced. So most likely by the time you graduate, what you're working on is it's not probably at the peak, or it's already going down, but it's a topic that you're very familiar with, where you can advise students. So you don't want to abandon that because you already have a track record, and that's where you can supervise students to publish. And keeping publishing record is important. At the same time, you want to explore new topics, because so that in the first, probably at the beginning, you keep publishing an old topic until you get a new topic. So there's a smooth transition. You don't want to stop and wait and go. So I think just to have a balanced portfolio. Yeah. Okay.
Because I guess when you start off, you can have 2 or 3 PhD students. So would a good strategy be to have one student that works, on a more risky topic, and then the other 2 that are a little bit in safer topics, or how would you do that?
in my case, I try to keep a group that is more balanced in terms of senior versus junior students. So the senior students or postdoc, actually, they are they can explore because they already have something on their record, and they can collaborate with junior students to supervise students. So it's helpful for both. Then they can explore some new topics. So I guess the same thing for assistant professors is that you want to keep something safe and then doing the exploration.
Yeah, I also want to add that initially when you are assistant professors, it's also beneficial that you collaborate with other assistant professors, right? Maybe your peers that you graduate from the same lab, but now you can collaborate with maybe with our senior co-authors. And maybe this group of young faculty are actually very energetic and think on the same pace. So they are already trained, better trained compared with your new PhD students. So it might be good for, among these young researchers to identify new topics. So offload the risk from the junior PhD student. And once you maybe develop the first one or two papers, you feel you are confident and you can bring students in.
Any questions? I guess I still have several questions on the list, and also I guess suggest we may also break up and just if you want to feel more comfortable talking in person, will be available if you want to ask some questions. So what do you prefer? Like let me I guess before we break out, who has a question that we want to have all the panelists here and have a discussion? Last chance for questions. All right. You don't need to talk, just raise your hand. You prefer that we break out into small, so we'll just do more informally. We'll be here and you can talk. Who prefer that? No? Who prefer to have a break now? So the schedule is that we're going to be stopping at 3:15, then take a half an hour break, then come back for another plenary talk. So there will be a 30 minutes break. I guess let's continue with several other questions. Let's see. Then we'll, now it's 3:08. Nobody raised their hands. Yeah. Yeah. Now, I guess we'll just have two more questions, and we'll break out to see, and we can start chatting. How to address possible bias and harassment? Or is this a question that you are interested in? Anybody will raise hand? Bias and harassment. Somebody is interested. Anybody wants to? Harry, you want to give a shot?
Yeah, I think you should. One thing you shouldn't do is leave it to yourself. Report it to. Yeah, don't just leave it to yourself. You report it to someone at the university. Usually, department has some set person point of contact. If you could either talk to your advisor if this is a person you trust, or there's often some point of contact in the department that you can go to report these issues. So university has Title IX offices that you can report these issues. I will highly suggest you to report this, not only for your own sort of mental health, but also keep a record of things, right? If later if this is a person potentially of a stage that has higher power than you, you don't want this power unbalancedness at someday come back so to haunt you. So having something, I think, in record will also help.
I think it's true for harassment. I guess bias is for harassment, what Yuejie said is absolutely true. You should report it. You should start by talking to someone that you trust on how to report it. It could be a senior female PhD student. It could be a different professor if you're dealing with, other than the person harassing. As far as bias, it's a very difficult situation. How do you even define bias? And I think at some level, each person is biased. The probability of the bias being zero is very low. So yeah, I don't have good answers on how to deal with bias. We've all dealt with it unknowingly, and I'm sure we've all been biased in a different way. So that's a whole different discussion.
So bias is often unconscious. So oftentimes the person who you feel is biased and he or she may not even aware. So I think communications is important. I had a department chair who's excellent, and he went through an SF training session on bias. He came back coming to us, say, I didn't know, I thought it was fair, but now I realize I had unconscious biasness. So I think just, I think in academia, many people are open-minded, just speak out and try to tell people how you feel. So you don't expect people to understand you if you don't speak out. So the same thing, if you don't ask questions, we cannot answer, right? So tell people how you feel. Okay.
Yeah, I agree. I think communication is very important. You have to communicate with people with whom you are comfortable. Obviously, you feel a sense of bias maybe because you're not able to ask that person or what the person was intending in their actions or what they say. Yeah, having a good communication with somebody whom you trust, and then maybe directly to the person also, if possible, then that will clear your for you, it will be clearer. So communicate. Don't feel shy about it. It is natural to feel shy, but I think you have to have that resolve it by communication.
Okay, any questions? Okay. Maybe you can share some experience of interdisciplinary research in the field of signal processing. Whatever you feel, yeah, in generic. How to branch out to different topics or working with people in other fields.
Yeah, I guess I had some experience working on sort of interdisciplinary topics. I guess the one that started closest to signal processing is the super resolution imaging project I had with some of the computational biology person, where we were basically trying to design better algorithms for the so-called STOM, this kind of fluorescence microscopy. Usually, I think this interdisciplinary research tends to be very difficult because we speak very different language, and we don't know what each other know, and we don't know what each other don't know. But on the other end, if each of the party is willing to sort of take a little bit of efforts to understand the other party's language, this helps a lot. And also, you need collaborators. The collaboration is most effective if both parties are willing to listen and adopt suggestions from the other side. So in my collaboration with that group, that was one of the, I think, my most successful collaboration, because they have very good listening ears that I use. So it's actually using some kind of compressive sensing technique to design the imaging algorithm. And from the algorithm inside, I told him basically, maybe if you collect measurements in a way that provides more diversity, maybe by putting more cameras, and each camera actually take less measurements. So in total, you still collect the same amount of data, But if you design your camera system in such a way, you can actually get better resolution images. He actually listened and he implemented the things, and it actually works out. And we had a paper on it. And on the other end, I have to listen to him how they set up the system so that I can actually give useful feedback and suggestion. And this is a really two-way sort of loop that you need to close the loop in order to make interdisciplinary research work. I also had experiences that may not be as successful, but in retrospect, I think I was in some sense too conservative or too lazy, that I didn't try to know enough about the other domain. And maybe both of us were like that way. So at the end, the intersection is too small or too narrow for us to make a real impact. But yeah, you do need to make all efforts. And sometimes that can mean that you make less impact in your own sort of core field. And that's really a trade-off depending on where you want to be.
Okay.
I don't have too much more to add. You just said that.
Okay. I guess I'll just ask the last question before. Anybody wants last call? Any question? Yeah. All right. I guess the last question is how to address excessive workload and how to set boundaries.
You have to be elastic. I think it's a personal choice, and it depends upon at what stage you are handling that situation. So it's a good idea to not go to a break point where everything collapses. So understand your time resources and your ability to pursue it. So be slightly more open. If it does not work out, it's okay. Okay, so don't be hard on yourself that the whole world will collapse if you are not able to do something. So I think you should, this is a bit difficult to teach. You have to experience it, and you'll have to, sometimes you will make some, you'll stick to something and then you'll hit a dead end, and then you will again go back and be more flexible next time. So it's a learning process.
Yeah, I think you need to learn to say no to a lot of things. A lot of the times we are measured by the maximum, right? If you do many different things, you are measured by the best that you achieve, right? The maximum of the signal, but not necessarily how many bins you have covered. I think there is some maybe literature or research suggested that women tend to actually say more yes than men. And often women tend to work on a lot of the maybe errands kind of things for the departments to do services, committee works that are often go unnoticed or unvalued at the end of the day. And we need to understand it's good to do some so that for the benefit of the good, sort of the good for the entire community, but you also need to know when to say no at some, especially when you grow your career. All of a sudden you realize you have too many on your plate that you can't even finish, and it's probably not a very healthy trend. So I would suggest that try to prioritize and only say yes to things that are important, that sort of add value, and try to sort of, you know, say more no's to the rest.
I totally agree with you. Definitely learn to say no early on. And I would say take on things that are either going to benefit your career or something you are really passionate about. If it's a particular committee that you are really interested in doing, then definitely do it. But don't just keep saying yes, because people will keep adding more. If you're a student, on the other hand, this is something I recently learned from a negative experience. Advisors, you know, if you keep doing the same thing, for me, something will take 30 minutes to code in. And I forget how long it would have taken me 20 years ago. So advisors often forget how they think they're giving you an hour of work. It may take, but it may actually take you a week to finish that work. let them know. They are not, often many people aren't doing it, aren't overloading you on purpose. They are thinking they're giving you an hour's work. And then they're wondering why it's taking you a week. They've forgotten that it would have taken them a week a long time ago. So tell your advisor that.
Yeah, those are good advices, good advice. So oftentimes we are the victim of our own success. You become more successful and you get more requests. So you need to learn to say no. On the other hand, when you're a student, when you feel it's excessive, try to talk with your advisor. Maybe just 10 minutes discussion with your advisor or your lab mate can help you to save 1 week of hard working on something that you cannot figure out. So try to balance when to ask questions. Yeah. All right, so we're getting to the end of the session. Any questions? Last call. Yes.
It's good for a junior faculty to have a mentor, and instead of directly saying no to your chair, for example, you can ask the mentor to intervene, and the mentor would maybe do it on your behalf with a better way.
Yeah, that's very good. Very true.
I would say a mentor is also very good when you want to complain about things.
All right, so I guess we'll have a coffee break. We'll be hanging around. So in case you have questions, feel free to ask any of us. So we'll come back 3:45, right? Okay. All right.
Hi, everyone. Welcome back. So in our last keynote speaker, last but not least, we are really happy and excited to have Dr. Yonina Eldar here with us. Dr. Eldar is a professor in the Department of Mathematics and Computer Science in the Weizmann Institute of Technology in Israel, where she heads the Center for Biomedical Engineering and Signal Processing and holds the Dorothy and Patrick Gorman Professional Chair. She's also a visiting professor at the MIT, a visiting scientist at the Broad Institute, and an adjunct professor at Duke University, and has been a visiting professor at Stanford. She's a member of the Israel Academy of Sciences and Humanities, and IEEE Fellow and a EuroCiv Fellow. She has received her BS degree in physics and BS degree in electrical engineering from Tel Aviv University and a PhD in electrical engineering and computer science from MIT. She has received many awards, including the IEEE Processing Society Technical Achievement Awards and really many, many more awards. She's also the editor-in-chief of Foundations and Trends Signal Processing and a member of several IEEE committees. Without further ado, Dr. Eldar, it's a great pleasure to have you with us today, and we're looking forward to your talk.
Thank you. Thank you so much. All right. So good afternoon, all the brave people that are here at this time instead of being by the beach. So it's really, really, really great to be here. And last year at ICASSP, I think, like you and me were there, right? There was some brave souls. So it's great. I literally just arrived like, I don't know, an hour ago, but it's great to see so many people. So I'm really looking forward to kind of a lot of interaction. Okay. So what I wanted to talk about today is how we could merge or potentially merge model-based ideas that we're used to in signal and image processing with deep learning. And of course, today, deep learning is everywhere. But what I believe before I start going into the details is that, signal processing or model-based, physics-based, everything we're used to actually has a huge role to play. So I know there's a lot of discussion and people saying, oh, AI is taking over everything. And, what's the role for signal processing? So actually, I think we have a huge role to play. And hopefully I'll convince you of that throughout this talk. So like we said, deep networks, of course, achieve, superior performance in many different areas. But if we look carefully, we'll see that actually most of the areas that are very successful are areas that didn't have necessarily very good models before. Okay, so probably, the two areas where deep learning is the most successful is vision problems, but huge vision problems, right? Where we have huge data sets that we could learn from. And of course, speech. And in both of those applications, there's two things in common. One is that we have huge data sets to learn from, and the other is that we didn't really have very good models before. Okay, so this is very different from some of the problems that we're used to looking at in signal processing. So, of course, we get great success. We could do crazy things, right? Like write poems, spawn faces. We could do more useful things, right? Like get very good detectors and classifiers, etc. But we know that, first of all, we have to get very, very large training sets in order to be successful. The training could be very computationally costly, and this is not practical if we have to keep on training. Okay, now think about it. If we look at, let's say, a network that was trained for a given SNR, very often if the SNR even changes a little bit, then we have to retrain, right? So the computational costs, usually we think of it in deep learning as an offline thing, but actually very often it's online, particularly if we're thinking about communication networks. Of course, it's very hard to get interpretability in general deep networks. And this also relates to the fact that it's not clear how robust the method is, how much they generalize. The complexity could be huge, right? If we look at GPT, there's billions of parameters. And of course, this is not practical when we think about signal processing problems. Okay, so this is some of the advantages, but of course, also the disadvantages of deep networks. Now, if we look at signal processing, right, which we all know and love, then signal processing, of course, is based on models. That's one of the first things we learn, is that we have to start with a model for our problem. The nice thing about a model is that we could incorporate anything we know about the problem. So we can incorporate any domain knowledge, we can incorporate structure, both in the model itself and in the inference model that we want. We know that we could get inference from relatively small amounts of data, so we don't need large data sets to succeed. And also the nice thing is that very often we have techniques that could tell us how well we're doing in retrospect and even a priori, right? We have bounds that tell us how well we could do even before we come up with a particular estimator. So these are some of the advantages of traditional signal processing. But of course, the disadvantage is that this relies on the fact that we have a very accurate model, which is often not the case. And also, even sometimes when we have a model, maybe there's an optimal thing that we could compute, but the computation may not be easy. Okay, so these are kind of the two things we'd like to overcome. And what we, and of course, many, many others in the community have been looking at in recent years, and I want to try and kind of summarize in the short talk, is how we could try and combine the two, how we could try and combine models with recent ideas of deep learning. Okay, so in order to see how we're going to do that before we kind of delve into the math, let's look at kind of a bird's eye view of signal processing and deep learning. And of course, this is kind of very, very generalized. But if we think of a standard signal processing problem, we start with a measurement. Okay, we're going to call it Y. We have some desired output X. So for example, this could be a noisy image and this could be a clean image, right? Or this could be, you know, the output of a radar system. And this is the target parameters that we want to try and find. And then we have some known relationship between what we measured and what we want. Okay, so we assume that what we measured Y is approximately some G of X. Okay, that's the starting point. We always have a model that we start with. And then once we have a model, we could come up with some metric function. So it could be a norm or it could be some other metric function that we want to optimize. And then you can use your favorite solver. So, you know, everyone has their own favorite solver. It could be gradient descent, ADMM, projective gradient, whatever, proximal gradient. So you take your favorite solver, you apply it to that model, and typically you'll get something like this. You'll get some pre-processing, some post-processing, and then you'll have these iterations where typically the iterations could be, at least conceptually, you could break them into two parts, a part that depends on the model and a part that's just some generic computation. Okay, so very roughly speaking, this is what a lot of signal processing algorithms end up looking like. Now, on the other hand, when you look at deep learning, or at least supervised deep learning, the setting is very, very different. So what you assume is that you have many paired inputs and outputs. You have a fixed architecture that you decide on advance. Okay, it's not necessarily related to your specific problem. It's some fixed architecture. Maybe it's a UNet or a ResNet or whatever, your favorite network that you want. And then what you're going to learn are these weights. So you take your training data, you learn the weights, and then when a new measurement comes in, you put it into the system and you hope that magically you will get something good. Okay, so this is kind of very roughly speaking how deep learning versus signal processing looks like. So how could we integrate the two? Again, there's many ways of doing this, but roughly speaking, we're going to look at two main techniques. So the first is unfolding or unrolling, which is a really nice idea that dates back to Gregor and Lacuna, and we'll explain it in the next few slides. So in unrolling, you basically use this optimization problem to give you the architecture itself. So you're going to infer using a network where the network resembles the optimization solver. A different technique that we're going to look at is a more data-driven hybrid method, where you actually don't infer using a network, you infer using the algorithm. But anywhere there's something that you don't know, you just replace that particular block with a network. Okay, and I'll explain both methods and when you may want to use each one of them. So those of you interested, we have a recent review where we go through this in more detail. And in fact, we have two recent books, one focused on wireless communications and one actually focused on medical applications, where we go into some of these ideas in more details in the context of those particular problems. So let's look at each one of these ideas in more detail, and then we'll go through various different applications. So the idea of unrolling actually dates back to a really beautiful paper of Gregor and LeCun from over a decade ago. But I would say only in the past few years has really been revisited, particularly by the signal processing and optimization community. So the idea is actually very simple, right? What we do in unfolding is we take our optimization problem we've seen before. And what we do is we first write down, let's say 10 steps of the algorithm, okay? A small number of steps of the algorithm. Now, we all know that if we take an iterative algorithm and apply it, let's say for 10 steps, typically we will not get a very good outcome, right? Usually you have to run iterative algorithms for thousands of iterations in order to get anything useful. But what we're going to do here is we're going to use 10 steps, okay? And I'm just saying 10 as example, but in most unfolding techniques, people don't use, more than 20 or 30 steps. So the point is that you use a small number. So up until here, there's no learning. But then in the last step, what we do is in each one of these iterations, there's parameters that depend on the model. And of course, the whole idea of using learning is that we assume that we don't necessarily know the entire model. So what we're going to do now is learn the parameters from data. Okay, so we end up getting a network that resembles our optimization solver, and it will depend both on the loss, the regularizer, and the particular solver that we chose. Okay, so for the same loss and regularizer, we could use different solvers, and that will lead to different networks. Okay, so this is in principle what unfolding looks like. And this is a recent review that we wrote on unfolding, particularly in the context of imaging, but we'll see some examples throughout the talk. So hopefully this at least gives you a sense of what we do in unfolding. The other technique that we look at is good for problems that don't actually follow from a very structured optimization formulation. So, and there's many examples in communication that we're going to look at later on. So, for example, if we think of dynamic programming or the Viterbi solver, right? It's not really, it originates from a maximum likelihood function, but it's not really directly minimizing some objective function. So there's many examples where we just have a good heuristic, right? Like, let's say the Viterbi algorithm, but it depends on things we don't know. Let's say the channel. So what we're going to do now is we're going to look at which block depends on something we don't know. And we're just going to replace that block by a very simple network. Okay, so it's just a very simple plug-in approach, but where we can show that in many cases, it's actually very useful and much better than learning end-to-end. So the advantage of these two methods is that, of course, they relate to the signal processing problem that we started off from, and it ends up giving us methods that are interpretable and much easier to analyze, and we'll talk more about that as we go through the talk. So just to kind of give a high-level view of what we said until now, we're basically looking for a middle ground between, these very abstract data-driven methods where we just throw everything we have at some network, and these very principled model-based networks, which both are trying to do the same thing, right? Both are trying to take an input and predict an output, but of course they're doing it in very different ways. And what we just said is that there's two general ways in which we can try and merge them. So we can look at things like the Viterbi detector or sparse recovery that are based on very principled model-based frameworks. And each one of those have equivalents that are just deep networks, right? So there's many papers, let's say, that look at imaging and replace the standard sparse recovery with some deep image recovery. There have been many papers that looked at how you do symbol detection using deep networks, right? So these are more generic deep network approaches applied to these problems. And what we're suggesting instead is to combine them, and we'll see each of these examples later on in the talk. So sparse recovery could be generalized to Lista. That's the unfolding method of Gregor and LeCun. And the Viterbi detector, the plug-in approach I described before, will lead to what we call the Viterbi net. And basically, these are two different approaches where we do one of two things. Either we infer using a deep network, but the model-based methods give us the architecture of the network. So that's what we do in the unfolding method. Or for using an algorithm like in the Viterbinet. So at the end, we're just using an algorithm, but the particular parts we don't know, we augment them with a neural network. Okay, so in both cases, we're capturing the signal processing structure in the problem, but embedding it in one way or another within these deep networks. Okay, so that's kind of the overall idea. And what I'm going to try to do in the rest of the talk is give you some concrete applications, which hopefully will make it a little bit more specific. And since it's a small crowd, I think it's fine. Feel free to kind of shoot questions as I'm going through. So if anything, I hope that's okay. Yeah, so sure, go ahead. Yeah, in one of the layers. So in a sense, unfolding is doing that. So unfolding is basically changing the generic layers into layers that are principled and coming from the signal processing formulation. Okay, so hopefully when we look at particular examples, that will be a little bit more clear, but that is the spirit of what we're doing here. Okay, so let's start we'll start with the unfolding techniques and go through them a little bit more slowly and then start looking at particular examples. So like I said before, the idea in unfolding is that we take some iterative algorithm, okay, that we're going to represent over here. So we have our input Y, it goes through some function, we get our current estimate X, and in a general iterative algorithm, you just apply this many, many times. So what we're going to do in unfolding is we apply this a finite number of times, okay, K times. But then each one of these layers, we're now going to think of them as parameterized by parameters, where in a standard iterative algorithm, those are fixed, right? The same layer is applied over and over again. In unfolding, we're going to think of these as parameters, and we're actually going to learn them from data. Okay, so that's how we're going to get different layers. So let's look, for example, at maybe, one of the most popular examples that have been looked at in signal processing, at least in the last decade, which is the sparse recovery problem. So we assume that we have, let's say, a linear Gaussian model where we have a sparse input observed through some linear transform with Gaussian noise. And then, one of the most popular methods to recover X is to use this least squares objective with an L1 sparsity. And if you just apply a simple proximal gradient algorithm to solve this problem, you end up getting the very famous iterative shrinkage and thresholding ISTA algorithm, which basically what it does in each iteration, it computes the gradient. So this is coming from the gradient where mu is the step size. And then you have this thresholding operator, which is coming from the proximal projection. Okay, so this is just a regular proximal gradient applied to this objective. And if you apply this many times, typically like, 10,000 times, you'll end up recovering a sparse input. Okay, so this is one of the most popular methods used for sparse recovery. Okay, so how would we turn this into a network? So now instead of applying this fixed iteration, 20,000 or 10,000 times, what we're going to do now is we're going to write this down a finite number of times, let's say 10 times. And now we could input different levels of learning, depending on what we know and what we don't know. So for example, if A is known entirely, if we know the forward model, then maybe we want to keep these fixed, just like they are over here, and only learn the lambda in each layer and the mu, the step size in each layer. So that's kind of the, minimal amount of learning. On the other hand, if we don't know A exactly, or we're not even sure that our data is really perfectly linear, then we could learn A as well, or we could just call these blocks W1 and W2 and learn them independently. Okay, so there's a lot of flexibility here in terms of how do we apply this. We could apply different levels of learning, but in all cases, we're getting an architecture that starts from our original problem formulation. And it's clear here that if there's anything we know about the problem, if we added another regularizer or change the metric, then we're going to get a different architecture. So the neural network that we get depends on the signal processing model and the signal processing metric that we started off with. Okay, so this is kind of a variation of the original idea of Gregor and LeCun, and it could be extended in many, many different ways. So one nice thing that you could do immediately is that once we have an optimization formulation of the problem, we could use, the many tools that have been developed in optimization to develop interesting new networks. So for example, one of the big issues that we all are aware of with networks is robustness, right? Like if the data changes a little bit, or if the test data and the training data were not the same, then we know that the networks are going to perform quite poorly. So here it's very natural to say, okay, since we're using an optimization formulation, why don't we use robust optimization to get a robust network? And that's very simple to do in a sense, right? Because the optimization formulation is already there. So there's been many, many works trying to robustify networks. And in some sense, they're very heuristic, right? Like you take a network and then there's all these tricks that are done to try to robustify them. What we're going to do here instead is say, no, let's just use the optimization formulation of robustness. So for example, one thing we could do is use what's known as robust lasso, where the idea is that we allow a perturbation to the forward model, and then we minimize both the error, the noise, but also the error in the forward model. Okay, so this is a well-known robust optimization formulation, and you can show that if you try to solve this minimization problem, then it's the same as solving almost the original problem we had before, but we have this extra scaling over here of the least squares objective. Okay, and again, this isn't heuristic, this follows from optimization. So now, instead of doing unfolding to the objective we had before, we could do unfolding to this new metric. Okay, so we end up getting a robust network, but we're not guessing it. It comes from the mathematical formulation. And not surprisingly, we can show that this new network that we get is in fact much more robust than standard networks. So if the test data and the training data are not the same, then we get much better performance using this network. And the nice thing is that, of course, here it's hard to see the details, but if you look at the paper, the actual network that we get is not something you would have guessed, okay? It has all these normalizations that look quite complicated, but at the end, we're not guessing them. They just follow from the optimization. So it's a very natural thing to do. And of course, now we could start having fun and start taking, the various things we know from optimization and applying them to deep networks. So, okay, I won't go into all the different variations, but hopefully you get the point. And what I want to do now is show various different applications where we've applied this in practice. So the first thing we looked at, and this is work that we did with Vishal Monga and his students, was saying, okay, could we use this very, very simple idea to get image deblurring? Now, there's probably, I don't know, tens of thousands of papers on doing image deblurring with various different deep networks. So when we started off, our goal was not necessarily to be better than them, but to see if we could compete with them using something very, very simple that you could program, without having to know a lot about deep networks. So what we did was something very intuitive. We said, okay, let's start with an optimization problem. What's our optimization problem? We're going to look for features of the image that match features of the data, where we assume that the features are sparse. So we add an L1 regularizer on the features and an L2 regularizer on the unknown blurring kernel. Okay, so almost the simplest thing that you could think of doing, nothing too elaborate. And then this gives us the optimization formulation. And then we use variable splitting, which you could think of as ADMM for those who are more familiar with ADMM, to kind of unroll this method. We used 10 unrolled iterations and applied it to a well-known data set. So what you see over here are examples of this network. And again, it's a really simple network. You don't have to know deep networks in order to apply it. It's just, again, starting from the optimization formulation, 10 layers. We learned the parameters from data. And what you could see over here, hopefully you can see on the screen, we trained it over an existing data set that's used as the benchmark. And what's really cool is that you can see that it actually competes very well and actually performs better than state-of-the-art method, even though it's a very, very simple network, both in terms of, the metrics that people use, PSNR, ISNR, and SSIM, but also visually, you can see this is our method over here. You can see that you get much sharper features than competing deep networks, where the competing networks were trained over much larger data sets and, of course, had a lot of tweaking. Okay, so they have many, many parameters and much more tweaking, whereas our network really is just following from an optimization formulation without any tweaking. Yeah. No, the exact same. The exact same. The training and everything was done in the exact same way. Okay, just our network has much fewer parameters. The blur was the same. Yeah, we took it all from the same data set. Okay, so in what we did before, the problem was relatively simple. I mean, you could see in the type of data that we had, right? There was blur, but it was basically linear blur. And therefore, we were able to treat it using kind of relatively simple regularizers. But what we wanted to look at next is, what if we have much more complicated problems? Like, for example, we just have a missing area in an image. That's going to be hard to do with just a simple L1 or an L2. So here, what we thought of doing is to say, okay, let's still do the unfolding, but we'll also unfold the regularizer. So instead of assuming that the regularizer is fixed, like let's say L1 or L2, which is not powerful enough for more complicated problems, we could unfold the regularizer. So we can assume some parameterized form of a regularizer and just learn the parameters of the regularizer together with learning the forward model. So particularly here, we use what's known as normalizing flows. It's not so important. It's basically just a form of parameterizing a PDF. And we did the unfolding also on the regularizer, not just on the forward problem. And this already allowed us to treat much more difficult problems. So here you see, for example, clean images, different forms of corruption. So here we have very heavy noise. Here we have just a cropped part of the image. And here we have very heavy blur. And we're comparing our method, which again is a very simple unfolding approach, with much more sophisticated algorithms that are in the literature, which of course have many more parameters or trained on larger data sets, etc. So again, we see that we get very, very good results. And again, at least for me, the nice thing is that it really just follows from the same principles that we've always used in signal processing, with the extra twist that we learn these parameters instead of keeping them fixed. But we still end up with something that's interpretable. And if we want to make changes to it, we know how to do it because we know where it's coming from. Okay, so the next thing I want to show is how we applied this to more complicated problems. And one of the things that we're very interested in our group is medical imaging. And these are problems that are quite hard to model very specifically with nice equations. So one practical problem that we've been dealing with for several years is various different problems in ultrasound, where one of them is trying to separate blood flow from tissue. So when you do an ultrasound scan, there's a particular mode of ultrasound called contrast-enhanced ultrasound, which could be very powerful. The problem is that you're using the contrast to see the blood flow, but then you get very strong reflections from the tissue. Okay, so this is actually after separation, but you see here that the tissue is very strong, and what you're interested in is in the blood. So when they're on top of each other, it's very hard to see the blood flow. So there's been, many different approaches that people have used to try and separate them, SVD being the most popular, but it's just not powerful enough to do the separation. Here you see, for example, using SVD, you still don't see separated tissue and blood flow. So what we did here is trying to use this low rank plus sparse, which again is a very popular model that's been used in signal processing in the past decade. So the idea is to model the data as being composed of low rank plus sparse, but that wasn't powerful enough. So when we did that, we got this, it's better than this, but it's still not powerful enough. But then the next step was to unfold that. And again, the advantage when you do unfolding is that you don't really assume that the model is exact, right? You allow some flexibility. So just as a funny thing, we called this method Corona, which I don't know, actually in English, people don't use Corona so much, right? In Hebrew, COVID was called Corona. So anyways, this was before COVID, but yeah, so we laughed and our method went viral. But anyway, we published this right before COVID. But anyway, so again, the idea is just the same as before. We have a least squares objective. We have a low rank norm on the low rank part and a sparsity prior on the sparse part. And then we unfold it. And again, we unfolded a simple proximal gradient scheme. So I won't go through the details. These are just standard optimization details. But then we unfolded it and learned the parameters from data. And it actually worked really well. So this is true data where, this is what we start off with, and this is the separation. Now, of course, here there's no ground truth, right? All we can measure are the patients. I don't have ground truth, but you can look at the images and it really does look like it does a good job in doing the separation. Yeah. Yeah, we do. So we do use, sorry.
What if it's not, you cannot find?
Yeah, okay, so really good point. Yeah, that's a very good point. So we do use back propagation here when we do the actual learning. So what we do in practice is that if anything is not differentiable, we kind of smooth it. And actually, people have done this in sparse recovery anyway, for other reasons, because when it's not smooth, even the forward pass is not so easy. So we just use the same trick. Okay, we basically smooth the different regularizers, and that's powerful enough. The other important thing is that we never use more than 10 layers. I mean, I keep on saying 10 because really that's what we use. And when you only use a small number of layers, all of the problems of like vanishing gradients and all of these issues that you typically have in deep networks, they don't appear because just 10 layers are not enough for them to happen. So it also just takes care of a lot of the nitty-gritty details of deep learning that usually, become an issue. Here, because we have a small number of layers, it doesn't happen anyway.
Yes, you can save a lot of training data. So on what order can you save?
Sorry.
You can.
Yeah.
do a lot of training
So what, yeah, that's a good point. So I'll show some theoretical results at the end, but in practice, we've been able to train, with really like in this case over here. So here, there's no ground truth, right? So actually, this is an important, I mean, it's not what you asked, but to answer what you asked, I have to say that. So you could have asked, how do we train here? Because we have no ground truth to begin with, right? So that's actually interesting because what we assume the ground truth is the output of the optimization algorithm. So I say, okay, I'm going to take it, I'm going to run 20,000 steps of the optimization algorithm and treat that as my ground truth, right? Although the output is not so good. And first of all, the cool thing is that even though we use that as ground truth, it actually gives us a good result at the end. But here, let's say in terms of training data, we only use 2 patients. So each patient had 10 or 20 frames, but it's the same patient, right? So we only had 2 independent patients, each one having 20 frames. So really it's nothing, right? I mean, very, very small amounts of data, and still we get very good results. Yeah, so it's kind of cool. Okay, we can use this also for other things like subsampling. So I won't go into too much detail here. This, of course, relates to prior work that we've done in sub-nyquil sampling. But now, again, we could just make everything more powerful because we don't have to have such exact models. So besides just using it for separation, we've also used this to do very efficient sampling so that now instead of having the big ultrasound machine, we can actually do the sampling in the probe itself and send the data wirelessly to some remote machine. And, okay, well, this has sound that you can't hear, but anyways, that's Dr. Shaitai Manyoden. If you could hear him, you would hear him say all this medical stuff. Like he's scanning my student here now with this digital probe. So basically using this unfolding, we could get very fast recovery using small amounts of data. And what we're doing here is that the data is going directly from the probe to the local machine, to a remote machine, you'll see it in a second via the cloud, and to an iPad. So at the end, we don't need an ultrasound machine, we only need a probe thanks to these unfolding techniques. Now, the other nice thing is that once we have access to the data itself, so today on ultrasound machines, you don't have access to data, you only get the final image. Now that we know how to sample efficiently, we get access to the data. And once we have the data, we could do 2 interesting things. So one is we can say, okay, instead of using standard beamforming that everybody uses for ultrasound, for radar, or whatever, we could take that raw data, what we call channel data, and apply model-based beamforming to it. So we do the same thing, the same idea of unfolding, but to actually do the beamforming, and that gives us much clearer images. Okay, so this is the same data, but this is after we did model-based beamforming. So that's kind of one thing you could do. The other thing you can do, and this is a clinical study that we did where we did this on clinical data. So this was patients with breast cancer, and again, I won't go through the details here, but we worked with doctors here to see if it actually gives them clinically a better image, right? Because just because our metrics say it's better doesn't mean that clinically it's better. But actually, the doctors were very happy with the new images and thought that they were clinically more informative. The other thing we could do is that once we have the channel data, we can actually look for quantitative parameters. So today, if you think of ultrasound and some aspects of radar, they're very qualitative and not quantitative. We just get an image, but we don't know anything about the actual physical parameters. Now that we have access to the data, we could use the unfolding again to solve the wave equations. Now, people, of course, have thought before of solving wave equations to extract physical parameters. The problem is that the wave equations are super complicated, and therefore, first of all, you get very complicated equations that you can't solve in real time, and therefore it's not interesting. The other thing is that the wave equations are approximate, right? You approximate them as linear functions, etc., and they're not exact. So now what we could do is again apply unfolding on the raw data to solve these wave equations. And this is an example over here where you see it's the same data. So this is beamforming on the data. And this is solving the wave equations using this unfolding to get the quantitative parameters. And here specifically, we're looking at a speed of sound map. So you can see here, if you look at this image, you see several black regions, which, could be suspect of having a lesion and having some sort of tumor, but it's very hard to identify where exactly it is and if it is or is not a tumor. And these are cases where you would send the patient to a biopsy because it's just too hard to know. But on the other hand, if you look at the speed of sound map, then you see right away that the tissue in this area is different. And in fact, this is a patient with breast cancer where the lesion is in fact over here. So it's a really nice example. Well, not nice in terms of the patient having cancer, but given that that's the fact anyway, it's really nice in showing that by getting the quantitative parameters, you can get really informative, much better information than by just looking at an image. So basically, we could use unfolding in different ways. We can use it to be more efficient in the data acquisition. We can use it to solve different kinds of equations and not just getting images. Okay, so switching gears, we've used it for many other applications as well. I won't go through more and more examples, but let me just say we've used it, for example, in COVID-19 for detection from X-ray and from ultrasound to detect COVID. And here, when COVID started, we worked with several hospitals in Israel. Again, I'm sure every country had their challenges. In Israel, one of the big challenges, at least at the beginning, the first year, was really just the detection rate. So PCR took an awful long time, like 3 days, to detect the PCR. And for those of you who know Israelis are very impatient. So nobody would wait for their result. And then, people were sick and they would contaminate others. So they were desperately looking for a method that would give faster results. And we worked with several hospitals on detecting COVID from X-ray. And just to show you that it's not an easy task. So if you look at these X-rays, right? So some of them, like this looks pretty clear. This one looks pretty clear, but if you look at the results, actually, this is positive to COVID-19, even though it looks really clear, right? Whereas this is negative, although it looks pretty blurry. So it's not so easy to tell from X-ray itself, but using this model-based framework, we were able to get really good results, over 90% detection, and this was actually implemented in one of the biggest hospitals in Israel. So again, we're not replacing doctors, okay? We use this together with the radiologists. But once they got the output of the algorithm, they re-looked the image and very often changed their decision. So this is from X-ray. We did the same thing from ultrasound. I'll skip through that. Okay, so these were all kind of imaging examples. Another nice thing that we've looked at using unfolding from is super resolution. So there's been a lot of work in the community and by many people sitting here on super resolution in many different applications, right, using L1. And here what we wanted to do is to say, okay, could we do unfolding to go beyond what we could do today? So we've looked at this particularly both in microscopy and in ultrasound. And let me start with microscopy just to change gears a little bit since we've looked at ultrasound until now. So one of the basic problems in microscopy, which motivated a lot of work, and also, one of the famous results by Candace, is the fact that we're limited by the diffraction limit. So we can see details that are smaller than half the wavelength used for illumination, which means that if we're using an optical microscope, we can see cells and bacteria, but we won't be able to see proteins and small molecules. And this is just a limit of physics, right? It's not a limit of the particular microscope that we're using. In 2014, the Nobel Prize went to this really clever idea of super resolution using fluorescence microscopy. And the idea was to insert these fluorophores and then control their blinking so that now instead of taking a single high resolution image, which you can't do by the laws of physics, you can take thousands of exposures where in each one, there's only a small number of fluorophores that are blinking. Okay, so think of an image that really should have, many green points, but then you can't see them, they overlap. So instead you control the chemistry, and that's why the Nobel Prize was in chemistry. So you control the chemistry so that in each exposure, you only have, let's say, 3 blinking spots. And then, if it's sparse enough, they won't overlap. And then you can pinpoint them in each image and sum over all images. So this is a very clever method. It's used a lot and in fact won the Nobel Prize. But what you're basically doing here is you're changing spatial resolution for temporal resolution. Because now to get a single image, you have to have thousands of exposures. And you can no longer do, for example, live cell imaging. Okay, so you have to kill the cell in order to image it. So what we wanted to look at is whether we can use these unfolding methods together with sparse recovery to be able to do super resolution with only a small number of exposures. So in interest of time, I'll skip through the technical details. Again, it's basically sparse recovery techniques that we do unfolding, but the nice thing is that it really works well. So what we're showing here, this is simulation and this is real data. This is a diffraction limited, what you would see from a standard microscope. Since this is simulation, we have ground truth. This is what you get from the method behind the Nobel Prize using 12,000 frames. And this is what we get using our method using only 300 frames. Okay, so we can reduce 2 orders of magnitude and get even better results. It works really well on real data as well. And when we do the unfolding, we don't have to know any parameters of the microscope in advance. Okay, so this is very robust. We can use this in any microscope. We don't have to estimate the point spread function. So we get very high resolution, both in time and in space, without having to know anything about the underlying microscope. And now we've been collaborating with Professor Gilad Aran, who's a professor of chemistry at Weizmann, and he's been interested in T-cell activation, which is a very important part of cancer cells. But until now, they haven't been able to see the dynamics of T-cells in real time. So using these techniques, for the first time, we've been able to actually see the T-cell activation. And what's nice I guess for him, but also for us, is that he had a series of papers on like a hypothesis of what happens to the T cell during the dynamics. But of course, they were never able to see it, so it was only a hypothesis. And then he gave us the films and we did the super resolution. And lucky for both of us, it actually coincided with the papers that he wrote and what he expected to happen. So that was kind of cool. And again, those of you interested, we've been doing quite a bit of work on this with the Broad Institute on using these deep unrolled recovery methods for biological imaging. And the really nice thing again is that everything is interpretable. So you could correlate the results nicely with the different hypotheses that the biologist or the chemist had about the actual process. Okay, the last application I want to show here is to super resolution in ultrasound. So I mentioned before that one way to get better resolution is to use contrast agents. And many people are familiar with that from, let's say, MRI and CT. You could do something similar in ultrasound where you inject these gas microbubbles into the bloodstream. But the point is that these gas microbubbles have better contrast, so they reflect the signal better. Therefore, presumably, you could get a better image. The problem is that that doesn't actually work. So what happens is you get a brighter image. Okay, so this is actually a breast lesion. So this is a study we did on breast cancer patients. This is a breast lesion. If you use contrast agents and don't do any particular processing, then what you get is just a very bright image. Okay, so it's true that you get better contrast, but better contrast doesn't actually help you in terms of tumor detection. But then what we did is, again, we applied these unfolding sparse recovery techniques in the relevant domain. And now what's really cool is that you could actually see what you couldn't see before. So these are 3 patients with breast lesions. And here, this is the standard ultrasound with contrast, okay? But you see that you just see these black holes. You can't see within the black holes. So it actually didn't help you get better resolution. But then after we use these unfolding methods, we can actually fill in the details. And you see that these are 3 very different lesions. So here you see that it's very homogeneous, and that actually means that it's a benign tumor. Here you see that there's fluids inside, which means that it's not even a tumor, it's just a cyst. And here, unfortunately, this is actually a malignant tumor because you can see that it's very non-homogeneous and the edges are very rough, and that's indicative of a malignant tumor. So using these sparse recovery methods in an unfolded fashion, we were able to really get super resolution that you couldn't get before. Okay, so to kind of wrap up, because I think I'm going over time. So in total, we spoke about unfolding. The other method we mentioned for techniques that are not really based on optimization methods is using this plug-in approach, and that was particularly used in communication. So the reason is that a lot of the popular methods in communication are not actually optimization algorithms. So in signal processing, in imaging, a lot of the methods are based on very kind of principled optimization, whereas in communication, a lot of them are kind of heuristics, right? Like the Viterbi algorithm is dynamic programming, successive interference cancellation is a greedy method, right? So we wanted to see how we could apply these model-based methods to those kind of techniques as well. And here we use the more plug-in approach. So let's look, for example, at the Viterbi algorithm. Everyone here is familiar with it, so I don't have to introduce it. There's been many papers that looked at doing symbol detection using deep networks, where, of course, the idea is to just replace, the Viterbi algorithm with an end-to-end learning technique. And what we suggested to do instead is to go back to the Viterbi algorithm. If you look at it carefully, what you find is that you could think of it in 2 steps. There's a step that computes the likelihood in each iteration. And then there's the dynamic programming, right, the trellis, which actually does not depend on anything. It only depends on the output of the likelihood. Okay, so if, for example, you don't know the channel, there's no reason to replace this whole part, the dynamic programming approach, with the network. It's still perfectly valid. The only thing that you won't know how to compute is the likelihood. So what we do is, instead of it replacing everything with a deep network, we just use a network to compute the likelihood. And that's actually a very simple classification problem. So we could do that with a 1 or 2 layer network. But then the output is still plugged into the trellis algorithm. And this is what leads to what we call the Viterbi net. So this was work that we did together with Andrea Goldsmith. And the cool thing about this is that obviously it's still interpretable. It's very simple. And in fact, we showed that we can use this without having to add any extra symbols for training. So the standard precoder that you would have, preamble that you would have anywhere on the communication network is enough to do the training here. And the training is done on the fly. And what's nice is that we get the same, almost the same performance as you get from the Viterbi algorithm, as if you knew the channel, even though we don't know the channel. So it trains very rapidly and adapts very rapidly to the different channel conditions. So we could do this for many other methods in communication as well. So for example, we've looked at factor graph methods, which are very popular in communication. And here again, instead of replacing them with an end-to-end deep network, we only learned the factors themselves and then still kept the message passing algorithm because that doesn't depend on the channel. So we do message passing over a graph where we only learn the factors in the graph. We could do the same thing for interference cancellation. So again, we keep the greedy approach of interference cancellation, but we learn the likelihood of each individual symbol in order to guess who is the strongest. That is the only thing we learn from data, but we keep the overall structure of successive interference cancellation. And many, many more examples. Okay, so those of you interested, you could look at our book on this where we go into more detail. But the point is that we keep the underlying communication algorithm. We only learn what we need within the algorithm. We've done this for Kalman filtering as well, which leads to what we call the Kalman net. So maybe let me skip that. And I do want to end with a little bit of theory. So just one last example I'm going to show because we're excited about it. And actually, we're going to have a demo of this. Those of you who are interested, we'll have a live demo on Wednesday in the demo session. So we've used these ideas also for vital sign monitoring of patients going back to radar. And the idea is to use sparse recovery methods, but in this unfolded technique. And using that, we could use a very simple radar measure vital signs of multiple patients, well, not multiple people, they don't have to be patients, they don't have to be sick, multiple people in a room. So we just stick a radar on the ceiling and we can measure vital signs of multiple people. And again, we're going to have a live demo of this on Wednesday, so you're welcome to come and look at it. And we've been extending these, so these are partial results. So here, this is still very much work in progress, but we've been looking at whether we can use these types of ideas to try and go through the skull and be able to get very good maps of the brain. So this is, of course, much more difficult. So as you see, the results are not yet convincing, but it's work in progress. We do have this nice skull. So it's not a real skull, by the way. It's a phantom. But even the phantom costs like $30,000. I don't know if that's more or less expensive than a real skull, but anyways, but we have it in the lab and we're kind of playing around with these ideas. We've also been using this. So this is a cow's brain. Okay, that is cheap, that you could actually buy. We've been using the same ideas for drug delivery systems. So drug delivery today is typically done by gold nanoparticles, and we can use these same ideas to detect the nanoparticles within the tissue. So it's easier to show it on cow tissue than on human tissue. So we're starting with cow tissue, but hopefully eventually we'll be able to do this on humans as well. So just to wrap up with a little bit of theory and to substantiate some of the results that I've shown. So we kept on saying we get interpretable results. We could train with a small amount of data. We get good performance, et cetera, et cetera. We've seen that in many examples, but the question is, could we prove that? So of course, proving anything in deep networks is complicated, but actually the cool thing is that this is easier to prove than general deep networks, and that's because there's a lot of structure. So it makes the proofs easier as well. So in some recent results, together with my students and Miguel Rodriguez, we were able to show, for example, that using this model-based network, you actually do get a generalization error that's smaller than if you did not use a model-based network. And what's actually cool is that we can show that the generalization error decays as with the number of layers. Now that is super intuitive, right? We know that if we add more layers, the generalization error decays, but most of the results, actually all results that we're aware of, besides ours in the literature, don't capture that. So if you look at standard results in learning theory, the generalization error actually grows with the number of layers. So this is the first result that shows that it decays using this model-based network. And we also could get bounds on the number of training samples that we need. So this goes back to your question. Again, these are of course bounds, so they don't capture the finite sample effects. But in terms of bounds, we can show that we need orders of magnitude less data than non-model-based networks. Okay, so to wrap up, we tried to show how we could kind of bridge learning theory with signal processing. Hopefully, I've convinced you all that signal processing has a huge role, at least in my opinion, to play in these types of problems. I think it's very important we can get methods that are nice, that are interpretable, that we control, and we get the best of both worlds. We could do both signal processing and learning. There's much more to be done, of course, on the theory side. So if anyone is interested, we're definitely looking for collaborators on that. Those of you interested, we have a recent review that was just published, so you could go ahead and look at some of the details. And there's many details on my webpage. Of course, none of this would have been done without my amazing team of students and collaborators that I've had the pleasure to work with. And thank you very much for your attention. So if there's time, happy to take questions. Here.
For the data that you're using, you said you're only using 2 patients, right? Did you try it with more? And do you know how is this gonna behave with more patient, more data, as it's gonna be more complex? And you might need to have like a bigger network as well. So how this can fit?
Yeah, that's a really good question. So in that particular case, we really only had 2 patients to work with, but then later on we got more patients. So we tested it on other patients and showed that the same network worked well. We did do, I think that's what you suggested. So correct me if I misunderstood you, but I think what you suggested is to say, okay, let's say as we get more patients, could we retrain and see if we do better? So in that particular case, we actually did that. We only ended up having like 10 patients. So it's not like we had a huge amount, but when we retrained, we did not do better. And actually at some point we were doing worse. Okay. So it was like training on a small amount of patients was actually good. And it intuitively makes sense because there's not a lot of parameters, right? I mean, basically the model captures most of it and there's only a small number of parameters to play around with. So of course, like anything in learning, right, at the end, there is always some trial and error. It's not a fixed theory, right? There's always something to play around with. But from our experience, actually training on small data sets is better than training on large data sets. In this case, when you're using a very parameterized function.
Wonderful talk. I enjoyed it very much. And you talk about the distribution shift, which is a major issue that being talked in the machine learning community, and the formulation that you incorporate those kind of proactively to be able to cope with some of the shift. Are there kind of a limit in terms of how much shift you will be able to tolerate? And a related question is, would there be a graceful degradation when there's such shift? So is there a limit that we see a clip, or is there graceful degradation, and how much we can tolerate?
Yeah, really, really good question. Thank you. So I think the nice thing is that the answers to all of these questions are very similar to the answers you would get from optimization. So if you think of, let's put learning aside for a minute. If you think of robust optimization, you could ask the same question, right? Like if I have a problem and I try to make it robust, and there's different formulations of doing that. You could do min-max, you can add an error, but all of those will have the problem that if I make the uncertainty set too large, then the algorithm is just not going to be good on average, right? It's only going to be good for like the worst case. But if I make it too small, then it's not going to be robust, right? So in a sense, it's very similar to that. The advantage in some sense that we have is that when you're using standard robust optimization, you make a choice and you're kind of stuck with it, right? Here, we make a soft choice in the sense because it's a parameter that we actually learn from the data. So it will be affected by the type of data we train on, okay? If I train on something that's very diverse, then I'll have a method that's more robust, but for the nominal case, it won't be as good. So in some sense, it's the same trade-offs you would get from robust optimization, but a little bit less harsh because we are learning from the data. Okay, but it is still, of course, sensitive to what you learn from. So I think, I mean, this all raises, there's many open points here. I think in some sense, it's like there's some bi-level optimization going on here, right? Because I have, for any kind of class of uncertainty, then the unfolding will work quite well, but I don't necessarily know in advance how uncertain I am, right? So I'd want like, something on top of that, which a little bit relates to meta learning and hyperparameters and stuff like that. So we have been looking at that. It's more tricky, of course, but I think that's really the next step, right? Of doing like an unfolded by level kind of optimization.
Hi. So you said something about, can you hear me?
Yeah, sure.
Yeah. You said something about more training data resulting in worse results in in answering the previous question. Why would that happen?
Yeah, okay. I mean, not that, like, that should not be the conclusion of this talk.
Yeah.
So, that means like a particular comment or particular question. So don't misquote me out of this room. But yeah, no. So yeah, well, that has to do with all the overfitting, right? That you would get. So think about it again. I at least for me, it's always helpful to think of like standard optimization, right? If I have a small number of parameters, then I don't need, like, think of optimization before learning, right? Like very often we would have signal processing problems where we'd have, you know, let's say we don't know how to choose the regularization parameter, and then we would say, okay, let's look at a few examples and we'll use that to determine the regularization parameter. Now, if I only have one parameter and I look at many examples, then chances are I'm going to be off, right? Because I'm overfitting in a sense. Like if I only have a small number of examples that are roughly characterizing what I need, then I'll get a good choice of lambda. If I try too many options, then, you know, my lambda is going to go all over the place and I'll probably not get such a good choice. So that was just a particular comment because the number of samples was very small. Of course, if I have, you know, infinitely many samples, then I'm not going to lose by having many samples. The point, I think, is that the types of problems we're looking at are problems where you don't have infinitely many samples to begin with. Because if you do, right, if I have infinite data like Google or Facebook, then I could use, you know, your full blown, I don't know, transformer or whatever, and it will probably work fine, right? As long as I don't change any of the channel conditions. So to begin with, the types of problems we're looking at are either problems where the training data is not very large, or the reverse side of that, which is mathematically the same, that the conditions change, like SNR or whatever. So under the scenarios where conditions are going to be changing, or you don't have a lot of training data, in that case, overfitting the training data is not necessarily going to be better than training on a small sample set.
But that should be a
again, not as a mathematical statement, it's a particular answer to the ultrasound problem. But
sure, but that should be a function of the algorithm, right? So to prevent overfitting, if you have, you know, generalization terms, or if you have prior, you know, terms, you know.
Yeah, but I don't, again,
depend on the prior and the post and the
right,
the data.
Right. But we're going back to the case, like when you say things like prior, posterior, this implicitly assumes that I have large training sets from which I learn. To learn a PDF, I can't use 2 samples. Okay, so we're talking about really small numbers.
No, I don't mean Bayesian learning. I just mean the same effect, you know, in any model, you'll have something that depends on the new data that you're using and something that depends on the training data. So.
Right, but the training data is not necessarily uniform. That's the point. So you're implicitly assuming that the training data is coming from the same distribution, and then you would be correct. So that's, if the distribution is not varying, then that would be true. Then more samples are not going to harm me. But the point is that in these types of problems like ultrasound, right, different patients are not IID. Okay.
Okay.
So,
sure.
but that's the essence of it. So
But
I think
that should help with generalization, right?
But again, that goes back to big numbers. So not in small numbers. Okay. When you have small numbers, and it's a function at the end of, you know, the number of parameters that you're looking for, how sophisticated your model is, et cetera. But the play here is in very small numbers. It's not the standard setting of learning where things are converging asymptotically. And you're also not assuming IID. Okay. So again, this was an answer particularly for the ultrasound case. Now, I do want to emphasize it's a very important thing what you're saying. So of course, if my data is IID and I have large data sets, then obviously more data is always going to help me. But here, that particular example that you were referring to was an ultrasound example where every patient, in a sense, is a different model. Now, I can't model individuals, right? Like that's just not going to work. So we're trying to capture structure rather than capture PDF, right? So if you look at what we did there, we looked at like robust PCA, which anyways you like. So, so in that sense, right? But it's not trying to capture something Bayesian, because I wouldn't be able to do that from a small number of patients. I'm trying to capture structure, but I'm trying to capture, I would say, very dominant features in the structure. Like if I try to get fine structure, then I'm going to be off. Okay, because the fine structure is going to be different from patient to patient. So it's like I'm trying to get only global features that are robust enough across patients. Does that kind of make sense?
We can talk offline.
Okay, yeah, sure.
So what's the big benefits of using signal processing plus machine learning instead of just using like one very robust machine learning, even though, because I mean, I say that as machine learning, okay, is not always like interpretable, but in some case, it's not that we don't care about the interpretability of it, but the output of the network's not gonna change any life or anything. Like there's no impact on it. So why do we need that?
So first of all, you said like there's no impact, we don't care. So we're looking at problems where we do care, right? Like definitely medical imaging. Obviously, I care about the outcome, right? I think anybody going to a doctor wants to know why they made a particular decision, right? If we're thinking about radar, whether it's for, imaging, radar imaging or autonomous vehicles, or again, these are examples where you do very much care about the impact, right? It's not like, okay, if I mistake the dog for a cat, so nothing bad is going to happen. But if I'm, an autonomous vehicle and I made a wrong turn, then something bad will happen. So I think all of the examples we've been looking at are examples where, first of all, you do very much care about the outcome. I think that's kind of point number one. Point number two, there are examples, and this goes back to the previous question, where we won't typically have large training sets, or we won't have large IID training sets. Okay, so these are more examples, kind of, I would say, real life examples where things could vary very rapidly. Like if it's a communication problem, the channels change all the time. If it's radar, the same thing. If it's medical imaging, patients are very different from each other. And actually you care about the outliers. You don't care about the standard case that doctors, don't need machine learning for. So the types of problems we're looking at here, which I think are very representative of a lot of things people do in signal processing, is that you actually don't have a lot of training data. Again, IID training data. You want to be able to adapt to varying conditions, and you do very much care about the outcome. So those are the cases where I believe the models are actually very useful. And I think that's kind of where signal processing, right, plays a role to begin with. So the answer is kind of in the question, right? So just to summarize, I think, again, if you have massive amounts of training data, you don't care about interpretability, and, no big deal if you made a mistake, then you don't need model-based learning, right? I mean, standard learning, of course, works, right? We all know that. So what we're aiming at here are exactly the cases where things vary. You care about computational costs, right? You have to do things rapidly if you want to do them on the edge, for example. You care about the output. You want it to be interpretable. The output has an impact, and you don't have a lot of training data. So those are the scenarios where the model, and again, I think those are the scenarios where modeling and signal processing help traditionally, right? So I guess the way I view it is that, and again, sorry for kind of going off on, but when I started my career, I remember those were the days where kind of convex optimization for communication was like very, very hot, right? And I remember still as a student, I went to a tutorial of Tom Liu where he talked about, convex optimization for communication. And I remember people saying, oh, now there's not going to be anything to do in communication because you could just use a convex optimization solver and solve any problem, right? And of course, we know that's not true. It's another super important tool that we all have many papers on, how you use it. So in some sense, I view it the same way. I mean, learning is a super important tool, and obviously we want to embrace it. But at least to me, it's another tool in this big paradigm of, signal processing thinking. And just like optimization came along, I mean, it was always there, but at some point people started to embrace it within the community. And then it became an enabler for many things we couldn't do before. Now we have learning. But again, at least for me, we want to put it in the same framework, right? It's not instead of signal processing. It's together with. It's another tool that if we use, at least in my opinion, if we use appropriately within the framework of signal processing, we could do everything we did before, right? Just better. We have another tool that we can use. Yeah. So heat maps, okay. I mean, heat maps are interpretable in retrospect in the sense that they don't use an interpretable architecture. They don't a priori incorporate anything about the problem. You could use them only in retrospect, right? Like once you have a network, you could go back, and we did, if you look at our paper that's on COVID, we do compare there to heat maps, right? So you could go back and say, given the method, I could plot a heat map and see if it was doing what I expected it to do. So yeah, we do things like that, but heat maps are posteriori methods to analyze your network. They don't help you design a better network. All right. I'm happy to take more questions if anybody wants offline. So thank you.
Thank you, Dr. Eldar, for this wonderful presentation and very inspiring. So moving forward, we have our last session for today, and we will be doing, this will be done online. So maybe we could pull up our speaker. Okay, great. Okay, everyone. So now we'll move forward to the last part of our workshop today. First of all, we have Dr. Frarokh Atashzar today with us. That I would like. He's the chair of the Progress Committee, so he would like to give a small message, and then we're going to move forward to the awards that we have for some of our attendees. Dr. Atashzar, the floor is yours.
Thank you so much, Theodora and everybody, for organizing as an amazing event. And so I'm very sorry I couldn't be there physically. I really wish I could. There were some issues that I couldn't handle in terms of travel and being there physically. So anyways, I would like to give a few words. So I want to start by saying thanks everybody for being here today. So as we bring this event of the Progress Initiative in ICASSP in 2023 to a close, I would like to take a moment and acknowledge the significant stride we have made in fostering diversity and inclusivity in signal processing. The focus of Progress is clear and is critical from my point of view to encourage more women and minorities to pursue academic roles in signal processing. Our mission is not merely an ideal, but a duty we owe to the current and future generations of our field. The Progress Initiative is not just focused on providing opportunities to underrepresented groups, but also on encouraging the academic community to play an active role in developing and implementing guidelines and actions that promote diversity and inclusivity. This is an important aspect of the initiative, as it recognizes that promoting diversity requires fundamental changes and the involvement of all members of the academic community. Our discussions, presentation, and professional development activities at Progress have reminded us that promoting inclusivity and diversity is a shared responsibility. And I would like to repeat that it's a shared responsibility. And we all have a part to play in creating a more welcoming environment in the field. Progress aims to support individuals who may face unique challenges on their journey. We are in process of implementing a mentorship program, an important pillar of Progress that will provide valuable guidance to those starting their careers. The Progress Initiative is designed to shape the future of signal processing, providing a platform for discussion, learning, and connection, all targeted to promote diversity and inclusivity in signal processing. As we look ahead, let us remember this event as the springboard for ongoing effort in building a more diverse and inclusive community. I would like to express my heartfelt gratitude to our president, Athena Petropoulou, the amazing local chair who put a lot of effort in making this event a success, Theodora Kaspari, and our incredible colleagues who have played an essential role in making, again, this event a success. Professor Harry, Dr. Apaji, Vicky Zhao, Professor Flori, and Professor Zelatinsky. Besides great staff, SPS staff, Caroline Johnson, Teresa Agiropoulos. Also, I would like to thank Philipp Gramlich and his colleagues. Sorry if I pronounce your name incorrectly, and sorry if I miss anyone. So your contribution have truly enriched our initiative. As we conclude, let us all remember that this is just the beginning. We will continue to challenge the status, strive for change, and foster an inclusive community. Thank you for being part of this journey, and let us eagerly anticipate an exciting future. Thank you, and here is to our continued progress. And with that, I would like to give the mic back to Theodora and to conclude the session. Thank you, everybody.
Thank you so much. That was really inspiring. Thank you. And I wish you were here with us today. So now we're going to the last part of our workshop, which is about the awards. Dr. Petropoulou, our IEEE SPS president, will come to hand off the awards. I was wondering if I can share my screen. Oh, yeah. Perfect. Okay. So I hope people are here. Maybe we can start. And you should have the same order, hopefully. Yeah. Yeah. No.
So that the Signal Processing Society is pleased to provide grants of $1,000 in travel reimbursement. We're very excited that you could make it, whoever could make it, since it's reimbursement. We gave a priority to people who actually travel to this event. So, okay, so. But if you put the next one,
Okay. So
yes, so we have certificates for you. Aswini, Bamini. Okay. Congratulations. Darini Ragavan.
Fabian Ricardo Latorre Gomez. Jessica Sanders. Mobina Mumaraki. Shreya Gwanendra Upadhyay. I'm sorry if I confused. Salamata Konate. And last but not least, Wohan Shiwan Chen.